Hey everyone, today we will be continuing on our latent diffusion model implementation. So let's do a little bit of a recap. In part one, just a while back, we trained the LPIPS model. So when it comes to training our latent diffusion model, let's kind of pull up that picture again. This is right here. In latent diffusion, there's a couple of different parts that go into this. First, we have this this portion right here. This basically takes images from the pixel space, compresses it down, and decompresses it. So this is a type of an autoencoder, typically a variational autoencoder. And then this part right here is the actual diffusion model, which takes the latent space and does the generative process. And again, we really care about this because diffusion is really expensive, especially on high resolution images. So this cheapens the diffusion training process because we now get to train diffusion on this very small compressed latent space rather than the large image space. For example, if the original images are 512 by 512, typically we'd have to train the diffusion model at that 512 by 512 resolution, which is huge. On the other hand, in latent diffusion, we can take that 512 by 512 image, compress it down to something like 32 by 32, and then train our diffusion model on those tiny little 32 by 32 images, which is much more helpful and much cheaper. Now, obviously, to do this, we need to train this here. So this is why latent diffusion models have a two-stage training process. Stage one is training of the variational autoencoder. That's what we're going to focus on today. And then stage two is the training of the diffusion model, which won't look all that different from our previous diffusion tutorial. So as a prerequisite, I already assume you're comfortable with variational autoencoders. I have a whole video on my I actually have two videos on my channel that you can take a look at that I'll put down below. One that's the derivation of the elbow loss, basically the variational autoencoder loss function, and then another that's the implementation of the variational autoencoder. So go ahead and take a look at that. The inspiration for the code today mostly will be based on the AutoEncoder KL implementation from the diffusers, so like the Huggingface diffuser stuff. So that's where the inspiration for the code is coming from. And there's a couple things we're going to have to do. You can follow along, or you can basically train this model on anything you want. So there's two types of cases that we can do. Number one is we can train a unconditional model, right? That is basically our, you just have images and something like that. Or we can have a conditional model. And the conditional model is something like conceptual captions, right? So conceptual captions is a reasonably mid-size image data set. Basically, we have images and text pairs, so that's what makes it conditional, text conditional, because our goal in the end is to train a model that, you provide a prompt and it can generate an image that looks kind of like that prompt, right? That's what we're hoping to do. And so conceptual captions is exactly that. If you want to train just an unconditional one where it just generates pictures, then you can use Celeb or something like that. So we're going to spend a little bit of time at the beginning in the actual preparation of the conceptual captions dataset. It's not too hard, just a couple of steps here and there. And then after that, we will get into the VAE pre-training. And for the pre-training of the VAE, that's where the LPIPS and the PatchGAN that we implemented last time will come into play. So we'll recap that once we get there. So for now, let's go ahead and start right here. If you want to do it on conceptual captions, that's no problem. It's relatively simple to download this because of a package called image to dataset. So first, what you have to do is go to the conceptual captions webpage, and right here. And over here, they're going to have some stuff that you can download. It's like a train split, val split, and labels, which we don't really care about, but train split and val split is what we really care about. And basically what these splits provide is a TSV. So if we look right here, it'll provide this TSV file, like a CSV. Discard, that's fine. I don't know what that is. Right here. Oh, you know what? Maybe trying to open that. It's a huge document with like 3 million rows, so that probably was going to happen. That's fine. So what it is we have a caption, right? Cybernetic scene isolated on a white background. And then we have corresponding links, right? So these are just links. So, links to the images. And not all these images are valid. Some of the links might be broken. I think about a third or so of the links are broken, but that's fine. So that's what we need. Once you download that, you can use the image to dataset package, which is this awesome little package that can basically mass download. And they have some examples here as well. It takes about an hour to download the 3 million image text pairs that we have here. What 3 million images is nothing. Like most models are trained on this 5 billion parameter model, but they have some examples here of how you can use it. And I have my own script as well to do that. So in scripts, and then, or maybe not scripts, it's right here. Here we go, image to dataset. We give it the path to the TSV that we downloaded. I give it, and basically the input format is the TSV file. The URL column is just called URL. The caption column is just called caption. And I specify that I want the output folder to be a Parquet file. This is just so I can use my Huggingface dataset stuff really easily. So we'll see where that comes in just a second. After that, where do I want to save it? And then, stuff like that, process count, thread count, image size, that sort of stuff. Okay, so just to see what the output looks like, once you download it, you'll get like a train folder and a valve folder, however you save it. And you'll end up with all these Parquet files, right? All these Parquet files. And the reason I picked Parquet is because it makes it very simple to convert to a Huggingface dataset, which I like doing. So we're going to be writing this function here called prepcc, and it has essentially all of these arguments. I just put them in. I'll make it a little bit bigger. Put them in ahead of time, but basically where's the data, path to, where's the data we just downloaded, where do we want to save the prep data, the Huggingface, what's the clip model we want to use, we'll talk about it in just a second, cache directory, batch size, all that sort of stuff, right? D type, all that stuff. And then I go ahead and take my, the D type, I get the D type of the data that I want just for conversion, like how do I want to save it? And we're basically good to go at that point. So this is kind of our prep. And what you see here is we have a tokenizer and a text encoder. So because we're doing specifically a text to image model, we need our text to be tokenized and prepped. And there's kind of two ways we can go about this. One just taking less disk space than the other one. The first way is when we process our text, we can just tokenize it and just save those tokens and we're good to go. On the other hand, during training, those tokens need to be passed through a clip model or really any text model we want, but clip is the one that Stable Diffusion used, so that's the one that we're going to use. So we're going to have to pass it through a clip model, grab the text embeddings, and then those embeddings are actually the ones that are used in the model. So it's up to you if you want to extract the embeddings right now and then just save them. Which would use more disk space, but less training time because you don't have to inference the clip model over and over again, or vice versa. We can use less disk space, not inference the clip model, just store the tokens themselves, and then inference the clip model for every single batch during training time, right? So we can, it's just a decision. I just do it without because it actually doesn't take that long to inference these clip models, so it's not a big deal. Right here, we'll see the purpose of that in a bit. So I essentially grab all the Parquet files. So basically, where's my data? We have all those .parquet files like we saw. And then I can simply use load dataset, which is the Huggingface datasets load dataset. As a Parquet, here are all the Parquet files, number of processes, CPU workers, and then a cache directory. So if we look inside here, print dataset, the first of all, downloading takes about an hour, and then when you actually go to run this, it will take some time. I've also created a file right here called prepcc that already is running this with all my correct paths, right? So this is right for me. You'll have to update it obviously for your own system, but it's just all of these arguments, right? So I don't want to break my head too much over this stuff as it's unique for every person. So yeah, this will take some time because actually you have to cache the data as it's going through. But you can see we've downloaded about 3.3 million images, and we have all of these columns: caption, URL, key, all that stuff. The one we really care about is the, I believe the status column. I'll check in just a second. But this one basically tells us whether or not it was successfully downloaded or if the link was broken. If the link's broken, we're going to go ahead and filter those out, right? So we don't need any non-success images. And then the JPEG is what contains our image, and the caption is what contains our, text itself. So if we take a look at our data set real quick, let's just look at one sample for the first one. If we look at the first one, you'll see that, and we're just kind of exploring the data format here. You can see the very first image failed to download. And here's the URL, it failed to download, and so JPEG is none right here. Okay, fine. Let's look at the first image. I think that one was fine. You're going to see that the image is not actually stored as an array, but rather as this thing, right? And this is just bytes. Basically, it's stored as bytes. We need to convert the bytes into our arrays themselves, which is, not too big of a deal. So there's a couple steps of processing that needs to be done here. So let's go ahead and start with that. The first step is, of course, we downloaded all this data. Not all the data is valid. So we can do dataset is dataset.filter, lambda, examples, and we're going to do example status. Our status should be equal to success, right? We want only images that have, let's see, for example, status right here, success. So we want images that were successfully downloaded. Images that weren't downloaded, we don't really care about. So that's just this line right here. So we can just put it right there, right? And how many CPU workers you want to do this. No problem there. After that, we can go ahead and delete all the columns that we don't care about. We don't care about anything except for the caption and the JPEG. So we can do calls to remove is just call for call in dataset.column. Oh my god, I can't type dataset.column names train if call not in caption JPEG. So it's going to go ahead and give me all the columns that I don't care about, and we can do dataset is equal to dataset.remove columns calls to remove. All right, go ahead and delete those. Next up, we need to actually convert our image bytes to pill images, right? Because what we really want is pill, not the this like weird byte formats. That's relatively straightforward. I'm going to write a method up here, def bin to pill, binary to pill, examples. And all we're going to do is images will be empty list for image in examples JPEG. We're going to do image is equal to image.open and then bytes IO image, right? So we already imported from IO bytes IO, that converts it, and then image.open can actually open it, and we can do images.append image. And then examples image is equal to images return example. So we've created a new column called image that will have our actual images in them, like the pill images, rather than their bytes version essentially. So we can go ahead and run that. I can run that right here. Run this in batch mode, however many workers, and then once we're done, we can go ahead and delete the JPEG column, and we're good to go, right? Nothing too crazy. Next, and this is kind of, again, the option, if args.pre-encode text. If you want to do this, it's fine. We can basically store the embeddings, but it just requires a lot more disk space, so it's up to you. Dataset is going to be dataset.map. And actually, we haven't even written the method yet, so let's write that. So we need to write the embed text method. So that's relatively straightforward. We can do def embed text. It's going to be batch and rank. So rank is going to be which GPU do we want to do it on. So that's fine. So we can keep that. So device is going to be equal to f CUDA, and it's going to be rank or 0. Right, so depending on what we have, percent torch.CUDA.device count. So this will always make sure, which device are we working on. It'll go ahead and grab it from there. Because rank is from 0 to number of GPUs. If rank is not provided, then it's none and it defaults to 0 and we're good to go, right? Yeah. And then our text encoder .2 is equal to text encoder, or actually text encoder.to device. It's an in-place thing anyway, so we're good to go. Good. So now that we've gone ahead and done that, we can go ahead and try to inference, right? So we're going to do try captions is equal to tokenizer batch caption, right? That's the column that we want, right? So let's go ahead and do padding equals true, truncation equals true, return tensors is PT. And then in the original Stable Diffusion implementation, you'll see that the max length that they use is 77. So they don't use any more than 77 tokens. This means if the descriptions are longer than 77 tokens, then they'll get clipped off. But most of the descriptions are actually pretty short, so this shouldn't affect too much. I'm not exactly sure why they use 77. Maybe they took like the average length and just went with that. They just don't want super long ones, right? So with torch.nodegrad, with torch.autocast device, we're going to do outputs is the text encoder, and we're going to pass in those captions and just grab those last hidden states. And these last hidden states are the output of the clip model, basically those, the embeddings, the token embeddings of the clip model. And these are what we want to store, because this is what we'll do cross-attention with in the next video, right? Now, I'm not actually going to save them. We're going to compute them as we go and when we actually do it, but that's fine. And so our prepped outputs, we're going to do for output padding in zip outputs and then captions attention mask, right? So we're going to go ahead and grab, because the tokenizer will also provide an attention mask, right? So which tokens are padding, which ones are not padding, because we're doing it batch by batch, of course. So we're going to do num non padding is torch.sum padding. Remember, this is going to be a essentially for every sample, right? We're looping through it one at a time. We basically have a 0, 1 vector in the attention mask where 1 is not pad and 0 is pad. So we're just going to add up the number of things that are not padded. So that's going to be sum, because otherwise you're just adding a bunch of ones together. Our output is going to be output num non padded. We only need to keep the embeddings for the non-padding locations, right? So we can go ahead and do that there. And then our prepped outputs.append output, and we can then do batch encoded text is our prepped outputs, except, right? We can do print for some reason. I think I was just debugging, so I just have this in here, but that's fine. We'll leave it in here. Failed batch. And for these cases, I'm just going to paste this in here. We're going to go ahead. We need something, right? If it fails. So we're just going to say that this batch failed. So we're going to say it's none for all of them. And then we can go ahead and return batch. And the reason you see the set start method spawn here is this is the way that the datasets, Huggingface datasets recommends to get multi-GPU dataset processing to work, right? So it's not really a me thing, that's just what they say. So you'll see how that works out in just a second. What we do now is dataset.map. We'll have embed text batched equals true, batch size is equal to args.gpu batch size, and this will be a per GPU batch size, with rank is true, and proc is going to be torch.cuda.device count. So just use the full system, however many we have. There we go, right? And then after that, of course, not every sample will be successful, right? So first of all, once we're done, we don't actually need this captions column anymore technically, because, well, we've already processed the captions, right? They're already embedded, so we don't need the text anymore. We can delete it. And then if we have any nuns, right? So that means we had some failed batches, we can go ahead and get rid of those as well, right? Delete all of the nuns, and we're good to go. And now we can do a dataset.save to disk args.path to save, right? Just go ahead and save it. And that's basically it, right? Nothing too crazy. I do not want to run this actually for you because, of course, it's going to take a while. So we're going to comment that out and just do dataset is equal to load from disk args.path to save. So let's just look at the final process dataset. This should just work, I hope. Let's see here. This might take a second. There we go. In this case, we have our caption, because when I actually processed the dataset, I did not run this. I did not pre-encode the text just because I don't think I had the disk space for it, and I was too lazy to wait, so that's fine. So we have essentially 2.26 million images in our dataset of text and image pairs. Let's just look at one of those samples real quick. 0. Look at the first sample. And we can see it's a pill image, which looks good. And we have a caption, American football player looks downfield during yada, 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 right? Good. So that's it. That was our dataset prep. I don't want to go into it much more than that because, of course, the data prep is specific to the dataset that you're working with. But in this case, I'm doing this, so it should be fine. Okay, so now that we've prepped our, I've already prepped it ahead of time, but because we've already prepped it, up next, we need to actually write the dataset data loader. Once this piece is done, we'll actually get into the variational AutoEncoder. So this probably could have been its own video, but it's fine. We're going to get through this pretty quickly, as I'm just going to copy paste stuff, to be honest, just to make this is probably the least interesting part of this whole implementation. Dataset.py. So we're going to need all of, let's just start with this part. I'll just paste them and explain as we go because there's not too much interesting going on here. In terms of image transformations, the model I train will be 256 by 256 images, not too big, but reasonable enough for me to just do on my system here. And then we have essentially a couple of different interpolation modes. We're going to stick to bilinear. Our images, we just for some variety, regularization, that sort of stuff, we can add an option to do random resized crops, right? Just grab random crops of size 256 by 256 from our image. If the image is, well, smaller, or bigger than the 256 by 256 we want, we can do random flipping if we want to. And then for transformation, it's relatively simple. We're just going to scale everything between -1 and 1. That's it. So all images will be rescaled between -1 and 1. And so that's why we're using a mean and variance of, or mean and standard deviation of 0.5, right? Because we take a 0 to 1, we subtract 0.5, going -0.5 to 0.5, and then we divide by 0.5, the standard deviation, so it's -1 to 1. And so this is a simple image transformation for that. And all we need, essentially, is our conceptual captions. I have a couple other ones in my repo that you can take a look at for like a generic image data set that just has, a data set of like text image pairs, that sort of stuff. But for now, I'm just going to be working on the conceptual captions data set just for the videos. So that's fine. Conceptual captions path to data transforms. There we go. Data set is going to be load from disk path to data. And we're going to do def sample transforms. So this is that load from disk function from earlier, right? We just load the data like normal. And to do our transforms, we're going to, for every batch, we're going to do transformed images is going to be equal to, and it's just going to be, we're going to apply, we'll pass in the transforms right here. So it'll be transforms image for image in batch images. Oh, for image in batch images. We'll just loop through, apply this transform to each one of them, and we are good to go. And then we can do batch images is equal to transformed images batch.pop image. We don't need those anymore. And image. Okay, so that may be not my best way of doing it. I should have called this something else, but image is the original image. Images is my transformed images, so I'm popping out image. I should have called this like pixel values or something like that, but it's fine. Return batch. So this batch will have the caption and everything else, and we're good to go. And we can do dataset.set transform sample transform. So this way, every time we grab a batch of samples or a sample from my dataset, the Huggingface dataset, right, it will go ahead and apply this transformation to it. And we can now return dataset, and we only need the training split, right? So we're good to go there. I think that's, yeah, okay, good. So now we need the def conceptual captions collate function. We don't really care about this as much right now, but we will later, right? For the actual training of our the conditional model. Today there's no conditioning; it's just the variational AutoEncoder, but we need all this, so let's just go ahead and put it all down. I'll go ahead and do this. So model name. What's the model? Did we pre-encode the text and return captions if we want to, right? And we can do tokenizer is AutoTokenizer dot from pre-trained model name. There we go. And let's define our collate function. It's going to take in a batch. And this should be relatively straightforward. Images are easy, right? So images torch.stack b images for b in batch, right? So I'm just gonna, all the images by the transforms will already, make them all the same size because that's what my random cropping and stuff is doing. So all the images can just get stacked together and we're good to go. And now we're gonna do if return captions, if pre-encoded text, right? So if we've already pre-encoded the text, there's really not a lot for us to do. We can do if, we can do if encoded text not in, let's look at the first one, .key. So if encoded, so basically if we want to use pre-encoded text, but the pre-encoded text is not actually there, then we can go ahead and raise an exception, right? Because this just means that, hey, we didn't actually create the pre-encoded text, so that's not good. So sequence lens is going to be len. So we just need to grab each of these. Remember, each of these are going to essentially be a batch size of 1 by sequence length by embed dim. But of course, the sequence length for each one of these encoded texts will be slightly different. So we need to make sure we do the padding and all that sort of stuff. So we're going to sequence length is going to be len b encoded text for b in batch. There we go. And then text conditioning is equal to torch.tensor b encoded text for b in batch. Just go ahead and grab that text, right? So these are already our 1 by sequence length by e tensors, and so our text conditioning is finally then torch.nn.utils.rnn.pad sequence, right? Simple pad sequence, text conditioning, batch first equals true. And actually, now that I'm remembering, I don't think this has the 1. I think it's just sequence length by embed dim, and that's it, right? So it's not 1 by sequence, it's just sequence length by embed dim as far as I remember, right? So there we go. So this will basically create our final batch by sequence length by embed dim. But of course, because it's all concatenated together, because we concatenated samples together, some of these things are padding, right? So they're padded portions. And so because there's padding, we need to also create an attention mask, which we'll do in just a second. Else, right? So else, if caption not in batch 0.keys, right? So if we didn't pre-encode the text, then we're assuming that we have the caption here and not in batch 0.keys. Then we're going to go ahead and raise an exception here as well, right? So hey, we needed the caption. There you go. And we do exactly the same thing as before, but now instead of processing embeddings, which is what we had here, we just have the captions themselves, or the tokenized captions essentially, right? That's what we're doing here, tokenize them, concatenate them, and then just add some pad token IDs, as you see right here, padding value, pad token ID. Now that we have that, so those are the two options, right? And we can do attention mask is going to then be torch.nn.utils.rnn.pad sequence. It's going to be torch.ones s for s in sequence length. Batch first is true, and padding value is 0, and we'll make it a Boolean. So basically, ones for every valid thing, because that's the sequence length, and then it will pad everything else at 0, and this gives us basically a matrix that looks like 1, 1, 1, 0, 0, and then like, I don't know, 1, 1, 1, 1, 1, 1, and then another one could be like 1, 1, 1, 0, 0, 0. I don't know, anything, right? So we're basically, what are the actual sequence lengths, and then what are the padding portions, and those are set as zeros, and then this is converted to a Boolean, right? And so we can then do return images. Oh, spelled images wrong. Let me just copy this in. There we go. There you go. Images. These are images. We have our text conditioning. The text conditioning can either be, well, text, right? It can either be text or it can be text embeddings, or it can be the raw text tokens that need to be embedded, which we haven't done yet then, right? So that'll happen later. And that's it. Now, this is only if we want to return the captions. If we don't care about the captions, then we can do else return images. And we can return the collate function, just like that. And that's everything, right? So this is how we're going to collate. We will care more about this later. We care basically this is all we need right now because we're not doing any kind of conditioning. Okay, so let's double check right here. All right, yeah, let's do our def get dataset. So in my get dataset, I actually have a bunch of different datasets that my full repository supports, but we will keep it simple. So let me just copy this in, right? Because no one wants to see me type this. What dataset do I want? The path, num channels, random reset, everything we just talked about, just in one place, and that's all. We also have return classes because some datasets have class conditioning, like ImageNet has class conditioning. That sort of stuff. So we're not going to worry about all of those things. We're just going to do this one right here for our conceptual captions only. We're going to do if dataset is conceptual captions, which is what it should be, then that's what we're going to do. And let's also define our image transformation. So that's going to use that image transform from earlier. And that's basically it. So not everything, you can see not everything's being used. Because we don't really care about everything right now, as we're just doing, we're just keeping this simple, right? For some of the other data sets, we have to, you could take a look at the code and you'll see that there's just a little bit more involved. But after that, we can essentially just go ahead and return the data set, right? Just return the train set and the collate function, right? The collate function, specifically this one. Good. So again, this is just just to show, right, the original code that I'm basing this off of. Like I have this, we have this generic image loader, just for like if you have a data set full of images and like text files. If you're working on, so if you're working on the like Celeb or ImageNet or whatever, then you can use these generic ones. But we're just doing conceptual captions because everything's nicely packaged into that little parquet, right? Little Huggingface data set makes my life very simple. Well, let's just give this a test. If name is main, we can do path to conceptual is equal to, let me just paste this in. This is my path. You can change it to yours. And dataset collate function is going to be get dataset. Dataset is conceptual captions. Path to data is path to conceptual, and pre-encoded text is false, right? We didn't pre-encode the text, so there we go. And our loader is going to be Dataloader dataset. Let's say batch size is 2, and the collate function is our collate function, right? The one we wrote. So we can do print next iter loader, right? Let's just see what that gives us. Oh, dataset.py. There we go. See if there's a bug. Give that a second. Conceptual captions is pre-encoded. Oh, is it? Okay, 1 second. Let me set this to true. Oh, okay. Oh, okay. I guess I did pre-encode the text conditioning. Okay, that's my bad. I guess I just forgot. Okay, so we do have the text conditioning already embedded. So you can see these are my embeddings, and they're already padded with zeros for, you know, for like positions that are, you know, padding and all that. Okay, we're good to go then. So that's everything, right? We have our image tensor and we have our text embeddings, which are just like that. Let's do print. If we look quickly at our, this is going to be images dot shape. We should see 256 by 256 images with 3 channels. Yep, batch size of 2, 3, 256 by 256. So there we go. That is our that is our data set, nothing too crazy. So yeah, I guess I did save all of the pre-encoded text. Okay, I guess why would I have written that code if I didn't use it? It's just been a little bit of time since I've looked at this. Okay, good. So up next is going to be finally our variational autoencoder. So like I mentioned, let's do again a little recap right here. Let's pull you back up. So the variational autoencoder's job is to both compress and decompress our images, like taking pixel space data, pushing it to a latent space that's somewhat Gaussian. That's why it's a variational autoencoder. And then taking that kind of Gaussian representation, projecting back to the pixel space. This kind of means two things. First, the reason we're projecting to Gaussian is because if our latent space is somewhat Gaussian, the diffusion process should have an easier time to learn those representations. If the latent space was something like more complicated or annoying or not regularized at all, then, you know, the diffusion process might have more of a challenge to learn it. And you can take a look in my variational autoencoder video where we see exactly what the latent space kind of looks like. On the other hand, the variational autoencoder's job is also to take images and project it back to the pixel space. That means the actual generation. I mean, the diffusion model will do the generative process in the latent space, but the actual image that we see when we go to, you know, see what the generations look like, that's really dependent on the quality of this, right? How good is my decoder? Now we know that variational autoencoders have some issues with decoding. They typically lead to kind of blurry images, and that's because they're trying to interpolate this continuous latent space. And so how can we improve the generative ability of variational autoencoders? And that's exactly what we'll be working on today, essentially. The trick we use is what we talked about last time. In addition to the standard variational autoencoder loss and mean squared error loss, what else, you know, that whatever it may be, we're going to add in some perceptual loss functions, right? LPIPS is a good perceptual loss function, the one we implemented last time, and PatchGAN is another perceptual loss function that just uses the GAN loss to enforce that. And that's exactly what we'll be doing. And so just to kind of get to the end a little bit, just so it's clear. If we look at sample gens and look at our autoencoder, here's some generative, here's some images. Let's open this maybe in a new tab that we can zoom in. This is what the generation looks like with our variational autoencoder with no help. And you can see that the generations on the other side are meaningfully more blurry. They're kind of smooth. You can see all the texture and stuff is gone. And this is probably close to what you've seen when we saw, especially some of the earlier generative models that we've seen, like these diffusion models. They always led to people especially looking kind of smooth like this, right? Smoothed out. And so this is basically because we've added no kind of perceptual loss function. The model has minimized basically the mean squared error between this image and this image. And the mean squared error between these two images probably isn't that much. But mean squared error isn't a representative of the general quality of the image, like the texture in it and that sort of stuff. And so this is exactly why we add these additional perceptual loss functions in. The first one, so let's just see what it looks like when we actually add it in. Let's open a new tab. You'll see an immediate improvement, right? So you can see that there's like clear detail in the lips, in the, like we still maintain some of like the creases in the forehead. You just see some artifacting. This isn't, you know, the best trained model. It's probably undertrained, and these models are trained on significantly larger data sets than what I have here, but this is just an example. We can see like the hair detail is still maintained. So it's good. It's not perfect in the sense that this is a common error you see in kind of models like this. Notice how both eyes here are kind of blue or orange, but here they've kind of turned into like a blue and an orange, right? So a little bit of weirdness happening here and there, but overall, this is a marked improvement over the other one, right? So this is why we're going to add these in. We don't have to think about these loss functions just yet. We actually need to implement the entirety of the VAE. So let's start with that piece. And then once we get there, we'll again come back to this. All right, so it's time to go ahead and start implementing the variational autoencoder. To do this, there's a couple of things that I've already copied in. So I've copied in this config file. Now, I typically hate config files, but that's fine. There's a lot of pieces in this project, so It's easier just to have everything in one place. Basically, they're just simple YAML files. We'll be loading these later to kind of define the structure of the model, but this is the default structure that we'll be using. Like what's the image size, input channels, output channels, latent channels, all that sort of stuff. So we'll see all of these things show up, and when we actually go to load the model, we can load it from this specific config file. In the same way, we'll have our configs for the UNET, but we won't be looking at any of this stuff today, right? That'll be next time. So for today, we're just going to look at essentially these things. And so to implement a variational autoencoder, let's kind of do a really quick recap. I made this figure just so it's clear. Normally in a variational autoencoder, it's basically just a standard autoencoder where we have some input, we have some reconstruction, and then our loss functions will be this reconstruction loss. We want the input to look like the output, right? Because otherwise it's not good. This is typically like mean squared error or L1 loss or something like that. And then we also want to regularize the latent space, right? We want to make sure the latent space is somewhat Gaussian. And so we add the KL divergence loss, right? The elbow loss. It's basically our penalty to make sure that this latent space is somewhat Gaussian. Again, all of this should be familiar if you've already seen the VAE video. And so what we're going to do is essentially implement this. And to implement it, it's relatively straightforward. What we need is essentially downsampling, right? We need to take an image, downsample it a couple times, and take an image and upsample it a couple times. And that's what we're going to work on first. So let's go ahead and write some of these base layers. Now this whole notion of downsampling, upsampling, we need it now, and we'll need it again later for the UNET, right? So we're going to just write some code that will be used again later on. So import torch, let's make it a little bit bigger. Import torch.nn as nn, and import torch.nn.functional as f. So we're going to need to write a upsample block 2D layers, right? We're working with images. Class upsample, or this will be class downsample block 2D, right? So this will be our downsample block, nn.module. And, oh, I wish it wasn't doing that. Okay, there we go. And then class residual block 2D, right? We want residual connections as well. Okay, good. So these are the three things we're going to be working on now. And so let's just start with the easy ones, upsample and downsample. To do our upsample block, it'll be def init. It's going to take self. How many input channels is this taking? What is the kernel size? We're going to say it's 3 by default, and upsample factor is 2. So we're always going to up and downsample by factors of 2. So if we start with a 256 by 256 image, when we downsample, we'll go down to 128, 64, 32, and then when we upsample, we'll go from 32 back to 64, back to 128, back to 256, that sort of stuff. And so when we do this, I'm going to make sure of one thing. In the up and downsample block, we never want our number of channels to change. We'll have, essentially, if we're passing in a tensor with 10 channels, then it will output 10 channels as well. It's just the spatial dimension will be upsampled or downsampled by their corresponding factor. So we can do super.init self. There we go, super.init. And we can do self.inChannels is inChannel self.kernel size is our kernel size, and self.factor, it will be the upsample factor, right? And to upsample, it'll be pretty straightforward. So there's two ways we can do upsampling. One way is doing a transpose convolution. That would be fine, but that typically leads to a tiling effect, right? So you'll kind of get this weird tile. If you look like the tiling effect for transpose convolutions, you'll see a bunch of blog posts about it, but at least there's weird tiling effect. So the more typical way of doing upsampling is we do a standard nn.upsample. So we use some type of upsampling method, bilinear, nearest, whatever it may be. So scale factor is our upsample factor, and let's say mode in the AutoEncoder KL implementation, they use nearest, right? So we're going to use nearest neighbor upsampling. So this line here is going to go ahead and take our image and upsample by a factor of whatever we provide. But then we're going to do a convolution after that, so we can do actually learn something. So in channels, because we don't change. The kernel size will be the kernel size, and then stride is 1, padding is same. So we upsample by a factor of 2, or whatever the upsample factor is, and then we do a learned convolution afterwards that no longer changes the image size, right? So the height and width resolution stay the same. We change absolutely nothing. We just project it up. And that's basically it. That's a standard way of doing upsampling for generative tasks. And it seems to lead to better downstream performance because it doesn't have that, again, that blotchy tiling effect. Batch channels, height, width is x.shape. Our upsample is going to be self.upsample. It's going to go through this upsample block. And then what we can do is just assert that the upsampled, so it's, batch channels height width. So the height and width of upsampled dot shape should equal to height times self dot factor and width times self dot factor, right? Because if we've properly upsampled by a factor of 2, then this is what we'd expect to see on the other end. And we can return upsampled. Our downsampled block is identical, right? So I can actually just copy this in because there's nothing really changes. The only thing that changes is this. When we downsample, we no longer need to use an upsampling block or anything. We don't need to upsample like this. To downsample, it's pretty straightforward. We can just do a strided convolution, right? So basically, if we want to downsample by a factor of 2, we'll use a stride of 2. And by using a stride of 2, we essentially downsample by a factor of 2 or whatever the downsample factor is. Nothing else changes, right? So it's just one convolution, and we just go ahead and downsample with a strided convolution, and we are good to go. That's our downsample block. Now for the residual block, and this is where it becomes a little bit more complicated because, like I mentioned, we want to use this residual block later for the UNET as well. If you remind yourself, in our diffusion implementation, we need to do something called the time embeddings, right? So in diffusion, and let me maybe just pull this up so it's clear. Should have had this up earlier. Diffuse. So in our diffusion, right here. So in our diffusion implementation, let's just be clear. And so this is standard diffusion, not latent diffusion. So this basically just has the implementation of the UNET. But we want to write a layer right now that works for both the variational encoder and the UNET just for simplicity, right? I mean, we could have written 2 different ones, but why make the code more complicated than it needs to be? So if you remember in diffusion, we have the sinusoidal time embeddings, right? This time embedding portion. And the goal is essentially, as our model is generating, remember, diffusion happens over, let's say, 1,000 time steps of diffusion, we need to tell our model which time step of noise are you currently at, right? And that's indicated by the time embeddings. We take these time embeddings, we do some projection on them if we want to, it's optional, and then we essentially add them to our UNET. So what it looks like is like this. In our residual block implementation, we see that we have these time embeddings, and we go ahead and grab our time embeddings and then add them to our tensor. This is what we're going to need to inject temporal information. What time step of denoising are we at? We need to inject that information in our residual blocks for the UNET later. We don't need it for the VAE. The VAE won't use any of this stuff, so we just need a toggle, right? We're going to be able to use this layer in both ways. So let's just go ahead and start implementing it, and I'll kind of point out the shapes and the pieces as we're going. Drop out P. Let me just copy this actually, the init, so I don't have to type out all these things. Basically, we have input channels, output channels. Dropout is fine. We're going to be doing group normalization. Seems to work a lot better than just batch norm, or almost as good as batch norm, but doesn't have the batch dependency, so that's good. And here's the extra stuff. We have our time embed. I'm going to get rid of all the class stuff just to simplify this a little bit more. We have our time embed projection. We have our time embed dim. And this is basically what's going to indicate, do we have temporal information coming in, those time embeddings coming in, or not? In the variational AutoEncoder, we don't care about it. This is going to stay false. In the UNET, we do care about it. That's where this will be true, right? So just keep that in mind. Super dot init. So first, self.norm 1. So the first thing we're going to do before we do anything else is a group normalization. Our num groups will be the group norm groups. Our num channels will be in channels. EPS will be the norm EPS, and we'll do an affine projection as well. This is just to match that AutoEncoder KL implementation. And then we're going to project this tensor with a convolution, conv 2D, from in channels to out channels to, and we're going to use a default kernel size 3, stride equals 2, and padding equals same. So all this is going to do is take our input tensor here and project it up to output channels, right? So we're going to normalize it first and then project it to output channels, but the spatial dimensions will remain identical, right? So we're not going to change the height and width. So there we go. That's the first set. And then we're going to have a second set of exactly the same thing. So I'm going to copy this in, right? So we're going to have a normalization, a dropout, and then a second convolution. And this convolution, the second one, is going to go from, because the first one outputs output channels, the second one will take out channels and then also go to out channels. So we're not going to change anything there. And there we go. Now for the time expansion. So self.time expand is none by default. We'll set it like that. And we're going to do if time embed proj. So if this is set to true, then we're going to do self.time expand is going to be a linear layer from time embed dim to out channels. Now, why are we doing this? So let's kind of set the shapes up. We're going to pass in a batch by channels, in channels, by height, by width, right? That's what's going to come in. Normalization doesn't change the shape, but the second convolution is going to take the batch by in channels by height by width and project it to batch by out channels by height by width. And there we go. Now our time embeddings, we won't be using them, but the time embeddings are going to be passed in as batch by our, let's see, time embed dim. So it's going to be for every single sample in the batch, we have a vector of length time embed dim, 1280 by default. We'll see this later. We have a vector that represents the temporal aspect of which time step of diffusion are we currently at, right? It's an embedding vector that represents that specific time step of diffusion. No problem. But this time embed dim may not be equal to output channels. So there's a little bit of a problem here. So what we're going to do is this linear layer is going to take this time embed dim and project it to batch by out channels. And then what you'll see is we're going to add some dummy dimensions of 1 by 1 here. And when we go to add this information in, it's going to be our, this data, this tensor right here of shape batch by out channels by height by width, and then our projected time data, which will be batch by, again, out channels by 1 by 1. So these two things can add together because we're essentially going to broadcast over the height and width dimension. So every single pixel, right, in the spatial dimension gets some temporal information added to it, right, along the channel dimension. And that's basically it. That's the key idea. We won't, again, need this today, but we're going to build it in just so we don't have to worry about it in the future. Next, we have our self.identity con. It's going to be nn.identity. So what is this? Remember, I shouldn't have deleted it. Our input channel is going to be batched by in channels by height by width. Our output of everything, once we're done, is going to be batched by out channels by height by width. But remember, this is a residual block. We want to add the input of this to the output. But if batch by in channels by height by width is a different shape than batch by out channels by height by width, because in channels does not equal to out channels, if these two things are not the same in channel dimension, then we can't just add things together, right? We can't sum things together that don't have the same shapes or is not broadcastable. So in this situation, all we need to do is just take our output and just project it back to the, we need to take the input channels and just project it to the output channels and perform that computation. So again, this computation only will happen if in channels does not equal to out channels. Only in this situation, we're going to do self.identityConv. It's going to be a super simple convolution with just a kernel size of 1 stride of 1, right? So very simple. So it's going to go from in channels to out channels. Kernel size is 1, stride equals 1. And this will just go ahead and project the input to the right shape so that addition can happen. And this will only again apply when in channels is not equal to out channels. So as simple as that. So now let's go ahead and write the forward method, self x we're going to have time embed. By default, it'll be none. And we're going to have, and that's it actually. Yeah, so we're good. All right, so just to start this off, residual connection, store a copy up ahead, and then we're going to perform all of our layers. So x is for self.norm1, x is f dot. So the CLU activation function seems to be the most popular for generative tasks like this, so we're going to stick to it. I'm sure there's other better ones maybe today, but we're going to stick to this for now. And so there we go. That's us passing our data through the first block. And so this is going to go from batch by in channels by height by width. And it's going to go to batch by out channels by height by width. No problem there. And now if time embed is not none, so if we're passing in some time embed, then we have to do a quick sanity check. If self.time expand is none, so if we pass in time embeddings, but this layer doesn't expect time embeddings, then we have an exception, right? So we'll just quickly throw that there, raise an exception. Otherwise we're good to go, right? We can do time embed is self.time expand, time embed. So again, this is going to go from batch by time embed dim, call it TED, to batch by out channels, right? So that's all this projection's doing, from time embedding dimension to the output channels. And then we'll have time embed is equal to time embed dot reshape, right? Reshape. And we're just going to keep the same time embed dot shape, but add 2 extra dummies. So it's basically unsqueeze minus 1, unsqueeze minus 1. We're just adding 2 1 dimensions here, just so it becomes by 1 by 1. And because now this has 4 channels, or 4 dimensions, we can easily just add it to this thing that also has 4 dimensions. So we're good to go. X plus time embed. And there we go. That's just adding that temporal information into it. Now that we've done all of that, x is self.norm2, x is, again, f.clu, one more time. X is self.dropout, x, and then x is self.con to x. And then finally, x is equal to x plus self.identityCon x residual connection. So basically just take our residual connection, the thing we stored ahead of time. If the channels are the same, there's no need to, this identity conv is literally just identity, so it won't do anything. If a projection is necessary, it'll project it, add it, and we are good to go. Return x. And there we go. So if you look at my code on my GitHub, you'll see that there's also class conditioning, but I'm not going to be making this more complicated than it needs to be. So I'm just simplifying it just a little bit, just so we can get through this quicker. And so there we go. That is our setup. Upsample, downsample, residual blocks. And of course, we're going to need this again for the VAE right now, but of course for the UNET again later. Another thing we need is attention, right? So in the VAE, they have attention blocks. And in the VAE, they actually just have attention, like just standard attention blocks. And we're going to write that today. In the UNET, there is full-on transformer blocks as well, right? So we're going to be writing all of the transformer stuff next time. For today, we're just going to stick to attention. Now, there's something that we need to keep in mind. So how do we do attention on images? Torch.nn as nn, and again, import torch.nn.functional as f. So what I mean by that is normally when we do attention on like sequence problems for our natural language tasks, for example, we have batch size by sequence length by embedding dimension. This is the typical shape of our data. How many samples do we have? What is the length? Number of tokens in every sample, and each token is represented by a vector of length e. On the other hand, images are batch sized by channels by height by width, right? That's the setup here. So how do we process this with attention? The way we do it is kind of imagining it this way. We say that height and width is our spatial dimension, right? Height and width is our spatial dimension. So this technically means we have height times width positions. So if our image is 10 by 10, right? Height and width is 10 by 10. That means there's 100 different positions, right, in that image. So it's height and width. And each position is represented by a vector of length c, the channel dimension. So we can then take this and transpose it, batch by height times width by c. And we treat our height times width, the number of pixels in that height width resolution, as the sequence length, that basically the number of pixels as like the number of quote unquote tokens. And each token is represented by a vector of length. Instead of e, it'll be the channel dimension. So this little conversion needs to happen. So we're going to do def image to sequence x. So this is basically going to take an image and convert it to that sequence dimension, just doing the reshape that I just mentioned. So batch by channels by height by width is x.shape, and x is going to be x.reshape. We're going to take batch by channels, but it's going to be height times width. Right? We're going to flatten those dimensions. And then we're going to transpose -1 and -2. So this will become a batch by height times width by channel dimension. And let's just put this doc string in there just so it's clear as you're looking at it. Right? So that's the conversion we just did. And we're going to return the sequence length, right? Or, whatever. It's not really a sequence, but the number of pixels is height times width. And we're going to return our x and the sequence length. And there we go. Very simple. In the same way, we want to be able to go back the other way, right? So we're going to write def sequence to image x, and we're going to pass in some image dim, which by default will be none. The reason we're doing this is if we have, let's say, batch by 20, or let's pick a different number. Let's pick 36 by, I don't know, 128. Well, this can mean a couple of things. This could have come from an image that's batch by 128 channels by 6 by 6, right? Because the 6 and 6 squared is 36, and the 128, so that's fine. But this could have equivalently come from something that's 12 and 3, right? What if our image is not square? We're only going to be dealing with square images for our intents and purposes, but we want to make this code as generic as possible, right? So if we pass in an image dim, then it's probably because the image itself is not square. So what we're going to do here is batch by sequence length by channels is going to be x.shape. That's the data we're passing in. If image dim is none, so if it's none, we're just going to assume that it's a square. So height is equal to width is equal to int sequence length 0.5, right? The square root of it. We're just going to assume it's a square if we don't pass it in. Otherwise, if we do pass something in, then height and width is going to be the image dim, right? We'll pass in that it's 12 by 6 or 12 by 3 or whatever. That's just a little, sanity check, but we don't need to worry about it too much as we're not dealing with non-square images for at least today. -1, -2, dot reshape. We're just going to put it back, right? Batch by channels by height by width. Just put it back and return x. And that's it, right? That's our quick, basically just going back and forth between our dimensions. Good. So now that we have that, we need to write attention. Now, this attention mechanism will look like almost every other attention mechanism out there, but we need to be able to do two different things. We need to have both self-attention, what we care about mostly today, and cross-attention. So if we go back to here, just pull up this picture again. There we go. In this image, we can see that we have conditioning, right? Conditioning is basically we want to condition our generative process on text or anything else really. It doesn't really matter, any kind of representation, but we'll be doing text conditioning later on. Well, if we want to do text conditioning, how do we actually condition it? And the way we do that is cross-attention. Basically, the queries is going to come from our image embeddings, right? The thing we're generating, so images. And our keys and values are going to come from the text embedding, the thing that we're going to be crossing with. So this is going to be cross-attention, right? We need to be able to implement, our attention mechanism needs to be able to do cross-attention between images and other inputs, other conditioning signals. But we only need that for the UNET. In the attention mechanism for our variational autoencoder, And we'll also need this in the UNET as well, but at least for now, what in the variational autoencoder, we only need to do self-attention. How are the different image pixels related to the other image pixels in the image, right? In that same image. So the queries, keys, and the values all come from the same source. And that's basically the difference. In cross-attention, our queries come from one source and the keys and values come from another source. And in self-attention, the queries, keys, and values all come from the exact same source. That's it. So that's the big idea. And so we just need an attention mechanism that can handle both of them. And I'll put this docstring in just so we can make it clear, right, with the shapes. Self-attention is going to be on just a source tensor. And that's it, right? Basically, we're going to reshape our image into the batch by height times width by channels. And then we're going to do self-attention on how are the different positions, spatial positions in this image related to other spatial positions in this image. In cross-attention, we have a source and a target. The source image is going to be our like text content, which will have some batch by, you know, the length of the text by some embedding dim. And then our target is going to be batched by height times width, right? Basically what we had before, batched by number of pixels by channels. And we need to then provide an attention mask, a padding mask for those text embeddings. And that's it. So we're going to essentially end up learning the relationship between the input and the output. If you're confused about any of this, because I'm going through it quite quickly, I have a whole video dedicated to, you know, building all the different versions of attention and that sort of stuff. So go ahead and watch that. Again, there's a little bit of a more of an expectation that you already know this stuff coming into this video, but that's okay. Right? Just go ahead and look at that. It's not very hard, and you can go from there. So what we're going to do is I'm going to paste in this piece right here, just so we can start this off. And this is kind of the same setup as always. So we have the embedding dimension of the source data. If this is true, that means we're doing cross-attention. If it's none, then we're not doing cross-attention, right? So that's how we're going to indicate, is this attention mechanism doing cross-attention or not doing cross-attention? We have our head dimension, right? So standard multi-head attention. We have our attention dropout, group norm again. Do we want a residual connection? This one comes from the, again, the AutoEncoder KL implementation. They have a residual connection built into the attention mechanism. So we'll add that in as well. Do we have a bias? And then the return shape. And this is kind of up to us, but I will kind of see where it comes in. But the return shape can either be 1D or 2D. Remember that when we do attention, if we pass in something that's batched by height times width by channel into the attention mechanism, it's going to output something with exactly the same shape, right? The attention mechanism doesn't change the shape of the data. If we pass in batch by height times width by channel, it'll output batch by height times width by channel. But now it's kind of up to us. Do we want to return it in this form, or do we want to convert it back to this form and then return it? So this is the 1D output, and this would have been the 2D output. And so it just gives us a little bit of control of the shape of the tensor that's being returned, right? I'm going to go ahead and just copy all of these little extra things in as well, just so I don't have to type it. So we're just storing everything. The return can either be 1D or 2D. We'll see how that plays in a bit. And then we have our attention head dimension, right? So how many heads of attention do we have? That sort of stuff. Okay, self.groupNorm groups is not none. So if we are including a group norm, then we, none. If we're doing that, if self.groupNorm groups is not none, then self.group norm is going to be nn.group, right? Standard group normalization. Num channels is the embedding dimension. Num groups is going to be the group norm groups, and EPS we'll just set to a default of like, I don't know, 1e minus 6, whatever. Okay. Good. So now we're going to do our attention projection. So KV input dim is going to be the embedding dimension if cross attention dim is none, else cross attention dim. So what you're seeing here is essentially, if we're doing self attention, I know that the input size of the embeddings, basically the channel, right, is going to be just our embedding dimension. So whatever I set here is going to be the input size, the number of channels in the image. It'll be the channel dimension, right? If we're doing cross attention, or actually let me take one step back. If we're doing that, this input size is going to be true for the queries, keys, and values, right? All queries, keys, and values will have all this. But if we're doing cross attention, I know the keys and values are going to come from the text embeddings. The text embeddings may have a different dimension. So like clip could have a dimension of, I don't know, like it could have a dimension of 1,000, let's say. So it could be different, right? Like the cross attention dim could be different. If we're doing cross attention, then the input dimension to my projections is going to be that, because we need to make sure when we do attention, everything has the same dimensionality. So we're gonna do self.qproj queries. Again, queries will always be images, is going to be nn.linear from embedding dimension to embedding dimension, bias equals bias. Self.kproj is going to be a linear layer, but this is going to go from kv input dimension to embedding dimension, bias equals bias, and then self.vproj, qkv, is going to be a linear layer with, again, kv input dim, embedding dimension, bias equals bias. So this will make sure, no matter what the source is, our keys and values are always projected to the same embedding dimension. It's just if the keys and values is for self-attention, then it'll just be embedding dimension to embedding dimension. But if the keys and values are coming from text embeddings, then whatever the dimensionality of the text embeddings are is what we'll be passing in here. And that will be from, the text embedding dim to the wanted embedding dimension. Once we have all this, then it's just standard attention. Self.outproj is going to be nn.linear. Again, from embedding dimension to embedding dimension, that'll be our post-attention projection. And that's basically it, right? Now let's go ahead and start writing, let's write a helper method. Check for reshape self images. This is just going to reshape our image dim to the sequence dim if we need to. So we're going to do if len images.shape for. So if the images are currently in the batch by channel, by height, by width, so all 4 dimensions, we're going to go ahead and just flatten them, right? Basically do that method we wrote earlier. Images num patches is image to sequence images, the thing we just wrote earlier. Else num patches is going to be equal to images.shape 1. So if it's not 4, then it must be 3. And if it's 3, then it'll be batched by num patches or num pixels by our by channel dimension, right? So we can just grab that here because there's already 3 dimensions, so we're good to go. And we can return images and num patches. So that's just a quick sanity check. So we're going to do def forward self attention, self images, pass, and then we're going to write another one, def forward cross attention self, and this is going to take images, some context, and an attention mask, which I'll set to none by default, right? Pass. So these are the 2 methods we need to write now. They're basically the same, so I'll write one and then I'll just kind of paste in the other one. So we're going to do batch size is going to be images.shape 0, images num patches is equal to self dot, we're just going to sanity check, self.check for reshape images. And then we do our projections. We're going to do q is self.qproj images. Right, so we're going to project our images. And then we're going to do dot reshape. And this is where we do multi-head, right? So right now, when we have it this way, it'll be in the batch by sequence length by embedding dim. We need to split that final embedding dimension into head dimensions and head dim. So we're going to reshape to, we'll leave the first dimensions alone. Batch size by num patches by self.num heads by self.head dim. So that's me splitting it up. After that, we're going to do a dot transpose 1, 2. So we're going to transpose this dimension and this dimension. So it becomes batch by number of heads by sequence length, num patches, by the head dim. And that's basically it, right? That's the first thing. And then we're just going to repeat this for K and V, right? K and V are the same thing. K, V. So again, I'm kind of going through the attention mechanism pretty quickly here because I again assume that you already know it. And again, I have a whole video dedicated to this if you want to learn more. So QKV, pass in our images, get our query key value projections, and we go ahead and set them up for multi-head attention. Our attention out is going to be equal to f dot. So we could have done the attention mechanism like normal, but we might as well use flash attention, right? Just to make our thing a little bit faster, right? Might as well. If self dot training, else 0.0, right? If we're in training mode, do dropout, non-training mode, 0 probability for dropout. So I'll go ahead and do our QK transpose over the square root of the embedding dim, softmax times the values. All that stuff is done for us right there, right? Very quick. And finally, attention out is going to be equal to our data. The output of attention is the same shape as the input, so it's going to be batched by num patches, by num heads, by head dim. That was the input. We're going to, and actually no, it was transposed, so let me just make it clear. It's going to be right here. We're currently at batch by heads by head dim, or sorry, heads by sequence length by head dim. And we're just going to put this back into batch by sequence length by embedding dim, where E is equal to head dim times the number of heads, right? That's the entire setup. So we would just go ahead and do that transpose again, 1, 2. That'll flip them back around to how they were. And then we'll do dot flatten 2, flatten the last 2 dimensions, or last 2 dimensions. So it'll be head dim and heads, flatten them, and you'll get E back, and we're good to go. We have this final output projection, the post-attention projection. We can add that in right here. Attention out is equal to self.outProj attention out, and we can return attention out. And that is our self-attention. Our cross-attention is exactly the same thing. So let's go ahead and do it. We're going to do images num patches. This is again self.check for reshape images. Remember, our queries Q is going to come from self.qproj, so this will be this line again. So our queries is identical, right? This will be the query comes from images, oh my god, I spelled everything wrong, comes from images. Our keys, values, come from context. And the context is again in the shape of batch by sequence length, call L, by our context embedding dim, right? So whatever the embedding dim of the context tensor is, depends on the text embeddings that clip provides us later on. And so this will basically be batch by context len by embed dim. The context embed dim is going to be context dot shape. And we'll now do K is, again, these 2 lines will be identical, right? So we can just paste these in. So K is just going to be the projection of the context, the keys projection of the context, and then the values will be the values projection of the context, and we're good to go. That's it. And now attention mask. Our attention mask by default is going to be passed in as a batch by L in this case, right? Sequence length. So we're going to have essentially for every single sample, we're going to have a vector of length L telling us which positions are actual text and which positions are just padding, right? We just added on extra pad tokens. So we're going to do if attention mask is not none, we need to take this and convert it to batch by 1 by L, sorry, let's see, num patches. So I'm going to call this num patches by text len. I'm going to call this text len just so it's clear. Right, this is the shape we need to project it to. The reason we're doing this is because flash attention expects the mask in this shape. Remember, in cross attention, we're learning how is every single patch of the image related to every single token of text, right? So our attention matrix is no longer necessarily square, right? Num patches and text length can be different lengths, right? So it may not be square, but that's okay. It doesn't really change anything in any meaningful way. So now that we have that, we need to take this and just kind of broadcast it to this shape. So that's pretty easy. If we do our attention mask, there we go. Attention mask is going to be equal to, just as a sanity check, we're going to pass it in like this. Actually, we already did in the Dataloader building, right? We made it bool, but just in case we don't. There we go. It's going to be equal to attention mask dot unsqueeze 1. So that's going to add a dimension right here. And then we're going to do unsqueeze 1 again. That'll add another dimension right here. And then we're going to do dot repeat. And we don't want to repeat this dimension or this dimension, so we're going to leave that as 1, 1. We want to repeat this dimension, num patches, number of times, as you can see. So it's going to be, repeat this one by num patches. And then we're going to do 1, right? So we, again, don't need to repeat the text length dimension again. And so this will finally give us, this takes the attention mask, makes it like this. There's no reason to do this. If we had implemented attention ourselves, we could have just done the broadcasting and we would have been good to go. And we wouldn't have to we wouldn't have to do any of this shape manipulation. But the PyTorch scaled.product attention, basically flash attention, expects the attention mask in this shape, right? So we want to make sure that we stick to that. Dropout P is going to be self dot, again, attention dropout, if self dot training else 0.0. And just like before, right, the rest of this is identical. So we'll reshape it back, project it with that post attention, and we're good to go. Good. Now let's write the actual forward method, and we just need to be able to toggle between self-attention and cross-attention depending on how we're passing in our inputs, right? So X, if context is none, that means we're doing self-attention. If context is not none, then we're doing cross-attention, right? Attention mask by default none. So we're going to store the residual here, X. This is a little bit extra. Normally attention doesn't have a residual connection, but the autoencoder KL did, and I'm trying to stay true to that, so we're going to keep it that way. If self.groupNorm groups is not none, so if we had a group normalization, we're going to pre-normalize our data. So there we go. Normalization doesn't change the shape of anything, so that's fine. If context is, forgot the comma right here. If context is none, so if we don't pass in cross attention, no problem. That means our attention out is going to be self.forward self-attention X, else attention out is going to be self.forward cross attention. We're going to pass in X, our context, and our attention mask, right? That will handle all of that for us. Now we're going to do if self.attention residual. So if we wanted a residual connection, this for the most part would be simple, but we just have to do a little bit of checking here. So remember, our data, our X, can be passed in two ways, right? It can be either batch by channels by height by width, or it can be batch by height times width by channel, right? Either of these are possible ways we can input in. And we're basically storing a copy of that. So we're going to do if our len attention out dot shape does not equal to len residual dot shape. So what this is saying, I know the output. I know the output of attention, or sorry, this should be attention out, my bad. The output of attention is going to have 3 dimensions, right? Because attention is always working on 3 dimensions, and I never took the attention out and reshaped it back into the 4 dimensions. So I know that this is always 3, but this one could be 3, the residual, right, my initial input, could be 3 or 4. So if my residual is all 4, well, then we have to do a quick check. If self.return shape is 1D, so if the return shape I want is just 1 dimensional, well, then let's just go ahead and fix it. So if we want 1D, that means attention out is correct. It's in the correct dimension, but this is still 2-dimensional. So we need to take this, convert it to 1 dimension, and then add it, right? So let's do that. So we're going to do if that, then we're going to do residual. We don't really care about the num things. It's going to be image to sequence residual. That's because I'm assuming, you know, we're doing square images and stuff like that. Else, if self.return shape is 2D, right? If we want a 2-dimensional thing, then I know that the residual is correct, right? And the attention out is always going to be in the 1D shape, right? Sequence length. So we need to take the attention out and put it back in the original shape. So it's going to be attention out is equal to sequence to image attention out. So again, if we want 1D, the residual needs to be shaped back to the correct 1D. If we want 2D, then the attention out needs to be shaped to 2D, right? So one or the other has to be flipped to the correct shape that we want. And that's basically it. And then we can do attention out is equal to attention out plus residual, that one residual connection. Else, right, if there is no residual, then it's up to us, right? So basically, we know the attention out's already 1D, but if we want 2D, then we have to do if self.return shape is 2D. That's fine. We can do attention out is equal to sequence to image attention out. Return attention out. And it's as simple as that, right? Nothing too crazy. Just a little bit of sanity checking, right? Because I know that this is always going to be in the 1D shape. This can be 1D or 2D. So we just need to make sure things are all lined up based on how we want to return it. So you can go through that, nothing too crazy. And that's it, right? That is our attention implementation. After this, transformers are not just attention. There's like the feed forward and the transformer block and all of that other stuff. But that's not really things we have to worry about today, right? Today we are focused on the variational autoencoder, which means we don't really care about any of that. So let's go ahead and start implementing the VAE. And we can finally have these imports because we have implemented them. In the init, I want to make sure I paste these things in. Let's see here. I don't need these. We haven't implemented these yet, right? These we'll do later. We haven't done the UNET, so we can get rid of all of U. We're about to do the VAE, so all of this will be implemented except for the VQ. We're going to ignore that. We don't need U yet. We don't need U yet. So we still have to implement a couple of these other things. Oh, I didn't do init waits. Okay, I'll come back to that later. So let's focus on this stuff right here for now. Okay, so VAE, very simple. There's actually not a lot of code to do here. It's mostly just wrapping all the stuff that we have done. So we need an encoder block 2D nn.module, and the encoder block is a downsampling block. So in our image, it's basically these, right? Things that encode. Decoder block will be the upsampling blocks. So we have our encoder block 2D. I will copy all of this in, sort of type it. So, you know, all the stuff that, none of this should seem new. It's everything we had. The only new thing is this, the number of residual blocks. Because what we've done earlier in this layer, we've defined these blocks, but now basically like a downsample block 2D. But the encoder block is 2 of them essentially, or however many we want. And so we just have to define them. So we're going to do super.init. And we're going to do self.blocks is going to be nn.module list, empty list. We're going to do for I in range num residual blocks, conv in channels is going to be in channels if I is 0. So the very first input will have in channels, but then after that, everything's going to be at out channels. So the first block of the 2 in this case, right here, the first block of the 2, will go from in channels to out channels, and then every block after that will just go from out channels to out channels. We won't change the channel dimension anymore. Yeah, okay, good. So that will be else out channels. And we're going to do self.blocks.append, and we first will do residual block 2D, and actually I'm just going to copy this in order to fill all this out, right? Oh, did I miss there we go. There you go. So basically we're going to append on all of these blocks, and notice that, and this doesn't exist here because I've simplified it. So we have time embedding is false because this is for the VAE, right? So there is no time embedding. And after that, we will have our self.downsample is equal to nn.identity. And we're going to do if add downsample. So at the end right here, add downsample, if add downsample. Self.downsample is equal to downsample block 2D, the one we've already written, from in channels is in channels. Downsample factor is our downsample factor, and our kernel size is our downsample kernel size. Very simple. Right, so that's it. So it's just a stack of a couple of residual blocks, however many we want, followed by an optional downsample block, which it's not really optional for us. We're going to need them, right? So we're going to have them. Def forward. Self x, again, time embed will be none by default because we don't really need them right now. for block in self dot blocks. We're going to do x is block x time embed, and then x is self dot downsample x return x, and that's it, right? That's us passing our data through one block of bunch of residual blocks and then this downsample block. Our decoder block is identical, so I'm just going to go ahead and paste it in, right? There's nothing different about this at all. Get rid of this one. The only thing that's changed is now instead of using a downsample block at the end, we have an upsample block, right? Because the decoder, as we saw, is basically these layers, things that take data and project it to higher dimensions, right? Or higher spatial dimensions. So we upsample our data. So it's an upsample block. Everything else is identical, right? Nothing else needs to be touched. And so now that we have all that, now we want to write something, and this comes basically from the AutoEncoder KL. They have, after all the residual blocks of the encoder, so basically after all of these things, right? They add something called the VAE Attention Residual Block. And then right at the start of the decoder, so right before this block right here, they also have a VAE Attention Residual Block. It's just like what we've had before. It's going to be a residual block like we have here, plus an attention block as well. So let's go ahead and add that in. So class VAE Attention Residual Block, and then dot module. Okay, I'll paste all this in again. So it's standard inputs, but the extra thing is attention. Actually, yeah, there's nothing extra in here. This is just a wrapper on everything we have. So we have self.resNets is going to be nn.module list. And self.attentions is again nn.module list, just like that. Self.res, so at the beginning, there has to always be one residual block. So one residual block 2D. So we basically started off like this. So this resnet will have at least one thing in it, but everything else could be empty if we don't have anything else. And then num layers identifies how many of these attention residual block combos we have. So we're going to do for blank in range num layers self.attentions.append, and I will just copy all of this again just so I don't have to type it out. Right, basically for every single layer, we're going to append on an attention block with the return shape as 2D because we're working with images, so it's convenient to leave it that way. And then we're going to have another residual block. So an attention, residual block, attention, residual block. So however many layers we specify. It depends on the depth, right? The more you have, bigger the model. Now, the forward method. Def forward, it's pretty straightforward. X time embed is none. We're going to do X is equal to, so there's always one resnet block, right? At the beginning. So self.resnet 0, pass in X, and then time embed is time embed. So that's always there for every single attention block. After that, we're going to loop through the remaining. So we're going to do for attention and res in zip self.attentions and self.resnets, but from 1 to the end, right? 1 to the end because we've already used the first one of these. So basically the remaining ones. We're going to do X is attention X, X is res X, time embed, return X. So that's it. That's just to make it close to the AutoEncoder KL implementation. They have this extra little block there. And so now that we have that, it's time to write the encoder, the decoder, the encoder decoder, and then the VAE itself, right? So our kind of home stretch, a lot of this code is very repetitive because it's just wrapping the stuff that we've already written. So VAE encoder, nn.module, def init. Here, I'll just copy all this in because it's just so much random stuff, right? And I'll get rid of this. That's clear. So yeah, we have here in the VAE encoder, so that's, these blocks right here, in case there's 3 of them. We have to specify how many input channels we have, how many output channels we have, double Z, we'll talk about that in just a second. We have how many channels per block. So basically this says that we have 4 blocks. each block is going to do a downsample by a factor of 2, except for the last one. And I'm only doing it that way because that's how, again, the AutoEncoder KL setup. So that means we're going to take a 3-channel image, project it to 128, and then the next block will go to 256, next block will go to 512, and the next block after that will go to 512. And of course, the more of these you have, the more downsampling you'll have, the bigger the model becomes, that sort of stuff. The other thing is that when we do these downsamplings, each of them will again downsample, because it's an encoder, by a factor of 2. So if our image starts at 256 by 256, this is going to take it to 128, then to 64, then to 32. But the last one will not change. So the last one won't do another downsample. This will keep it at 32 by 32. Again, that's just how they set it up there. And then all the other stuff is just stuff we had from before, right? How many attention layers, how many residual, if we want residual connections, residual layers for block, that sort of stuff, because we'll just be calling all the methods we just wrote up here, right? Just wrapping methods inside methods. Okay, so the first thing we need is self.conv in. It's going to be nn.conv2d in channels to in channels, out channels to self.channels per block 0. Right? We're going to go from 3 channels to the initial 128 channels, right? We're going to have kernel size is 3, stride is 1, padding is 1, just like that. And so that's the initial projection, just to take our data and project it to the dimensionality we want. And now we actually start our encoder blocks. So we're going to do self.encoder blocks as nn.module list. And the output channels is going to be self.channels per block 0. We're going to start it out there. Right? Start it out right here. And we're going to do for I channels in enumerate self.channels per block. In channels will be initially the out channels, right? So it'll be output channels. So the in channels will be initially 128 because that's where we started. And then our output channels will become is equal to self.channels per block I, right? Basically where are we at right now? Channels per block I. And then the last thing is final block is equal to I equal len self.channels per block -1. So we're just checking, is this the final block? If it is, then it'll be I will have the index of the last thing, right? Good. So now we can very simply do self.encoder blocks.append, and I'll just paste this in because no one wants to see me type this. There you go. It's just for every single one of these, we're going to append on one of these channels, right? And good. So yeah, I think that's, let's make sure. Okay. Yeah. Okay, good. Yeah, so that's everything. Now that we have that, after all of these blocks are done, like I mentioned, at the end of our encoder blocks is where we add that VAE attention residual block, right? That's just how the AutoEncoder KL is set up, so that's how we're going to set ours up too. I'll just keep pasting these things in because there's nothing interesting about them. It's just going to be this. Right, so after all of these things are done, we're going to go ahead and grab them right here. Right, so that's our VAE attention residual block. And then finally, we have our final output layer. So let's write these out. So our self.out norm is going to be nn. Again, another group normalization. Num channels is self.channels per block -1. Num groups is equal to group norm groups, and then EPS we'll set to 1e -6 as a default. And here's the important part. Conv out channels is going to be 2 times self.latent channels if double z, else self.latent channels. Okay, so this comes from here. So let's just quickly remind ourselves. In our implementation of the, here, let me find it real quick. In our implementation of the variational AutoEncoder, so if you remember back to that, or if you haven't seen it, again, that's a little bit of a prerequisite here. in our implementation of the VAE, remember the variational encoder works like this. Let's find that image. Where are you? Oh, right here. So in the VAE, after we encode, we project to predict our mean and log variance from which we sample a latent vector, right? That's the entire point of the VAE. We're sampling the latent vector, which then gets passed to the decoder. But for us to do this, it kind of works out this way. So if we remember in our encoder, right, we have essentially, after we pass it through the encoder, we have two different linear layers that go from mu will be a projection of the output of the encoder, and then log variance will be another projection of that. Right, so we have two different layers, and that's one way we could have done it, and that'd be totally fine. Another way we could have done it is mu and log var have the same dimensionality, right? So they're the same dimensionality. If what we can do with that then is that we could have just had one layer that projected to double the dimension, right? So instead of mu going from 32 to latent dim and a second one going from 32 to latent dim, we could have gone from 32 to 2 times the latent dim, and then just chunked it, right? We could have just taken half of the first output as the mu and then the second half as the log var, right? That'd be another way to do it. And I believe I did that in the, oh yeah, so I kind of do that here. So in our convolutional VAE, when we explored that, in the same way, we had a convolution that projected from self.bottleneck to self.bottleneck, right? So we had some output for mean and we had some other output for log var. Instead, what we could have done, instead of having two different convolutions, which is fine, we could have had one convolution, one that went from self.bottleneck to 2 times self.bottleneck. So our final dimensionality would be batch size by 2 times bottleneck by height by width, right? That would have been fine. And then we could have just chunked on that channel dimension. So that's what this is controlling, right? If we are doing double Z, that means we want 2 times the latent channel, so we can chunk it up. We need double Z for the purposes of our variational autoencoder. If we were doing the VQ VAE, which we won't be implementing in this video, but is in the Git repo, if we're doing VQ VAE, then we only need latent channels. We don't need double the amount because we're not doing any kind of sampling in the same way, right? So that's the only extra thing to keep in mind. So this, our intended output will be batched by the output of our, this, right? The final output at the end of our convolutions and all of that, the residual blocks will be batched by channels, by height, by width. And we need to get 2 different batch by latent channel. So I'll call this batch by latent channel, by height, by width. Well, we don't need one of them, we need 2 of them because we have our mean and the log variance, right? That's what we need for our variational autoencoder. But instead of having 2 different convolutions, we could just do 2 times this, right? Right here, just double it up. And then just take this and then chunk it, right? Just chunk it into 2, split the tensor into 2. And that's it, that's the only extra piece that we have here. So then we can do self.conv out is going to be nn.conv 2d self.channels per block, the last one, to conv out channels. Kernel size is 3 and padding is same. Right? Good. So that's it. That's the encoder, nothing crazy. And then our forward method is very simple. Self x is self.conv. And notice there's no time embedding or anything because that doesn't exist in our VAE portion of the model. For block in self.encoder blocks, x is block x is we have that attention block afterwards, and then we have x is self.out norm x is f.clu activation function, x is self.conv out, x return x. And that's it, right? That is our encoder. The decoder looks identical, right? So I'm just going to paste it in, right? I don't want to type all that again. The decoder is again identical. It's just a wrapper on everything we've had. So I'll just walk through it. Go to this. The decoder does all the same things, right? But now the input channels will just be based on, notice how we take the channels per block here and we reverse it around, right? Reverse it because our encoder goes from 128, 256, 512, 512. The decoder will go exactly in the opposite direction from 512, 512, 256, 128, right? Because the Autoencoders are typically set up as mirror images of each other, right? So we're just going to reverse it around. Our input channel is going to start from whatever the number of input channels are. In this case, it'll be our, whatever the in channels is set to. This will be based on our, the latent channels. So if the output of the latent here is 4, then the input would have been 4, whatever it may be. Okay, and so that's our latent channels. Got our input. We then have our attention block, just like before. So like I mentioned, they have the VAE attention block at the end of our encoder, but also at the beginning of the decoder, just so it's symmetrical, right? So we have that first. Then we have all our decoder blocks. We just go ahead and do our upsampling over and over again, and we're done, right? We just kind of output, we have another group norm, and then our final convolution output will output to however many output channels we have. If our image is a 3-channel image, then the final output of the autoencoder should also be 3 channels. And then we go ahead and forward it through exactly the same way, right? So nothing changed here. Next, just to again wrap all of these things together, I'm just going to keep pasting these so it's easy. So this is where the config comes in. So inside our config, we'll have all of these variables defined. They're again defined right here, right? So it's all of this stuff right here. But with this just makes it easier, right? We'll do it through a config file. And so here's the VAE encoder, VAE decoder. We have our encoder out channels depending on if we're doing double Z or not, right? And double Z depends on if we're quantizing, then we don't need double Z. We're not quantizing, so this is kind of extra code that we won't even be looking at. If we are quantizing, or if we're not quantizing, so if we're doing a standard variational autoencoder rather than a vector quantized variational autoencoder, then we need double Z, right? 2 times the latent channel. And some extra stuff that they add in is we can have a post-conv. So you can see right here, these are just things they had. Post-encoder latent proj, pre-decoder latent proj. Basically, it's just another convolution that you can optionally add, but right at the end of the encoder and right at the start of the decoder. It's optional. So, but they had it in the autoencoder KL, so I just tossed it in there. It's just another convolution, another place to learn. Forward encoder self x. X is self.encoder x. X is self.postEncoder conv x. And we can return x. Similarly, def forward decoder self x. It's going to be x is self.predecoder conv x. We first do that. And then x is self.decoder x. And we return x. And there we go. The reason I set it up like this is just so we can do a quick method. So we can write the VAE now. Class VAE. And the VAE is technically just a encoder decoder, right? It was just a wrapper on that. So we can do it here. Def init self config. And we can do super v self.init config, right? So we're basically initializing the encoder decoder whose init expects the config, which is why we also pass it in right here. And now what we can do is just write a standard VAE. And we already have all of these blocks and the forward and forward decoder available to us as methods, right? So we can just use those. So we can do self.config is config, just store that right here so we have access to it later. And so let's start with our encoding. So def encode self x return stats is false, and scale factor is none. We'll see what the scale factor is more later, not so much today, but we'll see what that is later. So we'll keep that in for now. So encoded is self.forward encoder, right? Forward encoder x. That will take our data, and this will encode it to a batch by 2 times L by height by width, right? So this is the double that we have. And so now that we've encoded, we need to chunk it. So we're going to do mu, and log var is torch.chunk encoded chunks equals 2 and dim equals 1. So we're going to split on the channel dimension to create mu and log var, and each mu and log var will be batched by L by height by width. It's not 2 times L. 2 times L is both of them. L just for each one. Now that we have that, we can do log var. This is a numerical stability thing. We're going to do clamp. Remember, we have to exponentiate this later. So we want to make sure that log var is between -30 and max of 20.0. So that's kind of the range of values that it can be, at least for float 32 and BF 32. If you're doing float 16, then you might have to fix that or find a different, find the correct range for those precision types. But we'll be doing BF 16 training, so it doesn't really matter. And now we need to write the sample z, mu, and log var. So remember, the entire point of all of this stuff, right, was we wanted to learn the mean and log variance and then sample the latent vector z. And we do that via the reparameterization trick, right? So you can see all of the derivations for that. But the reparameterization trick is pretty straightforward. We want data in the shape, or with the mean of A and the variance of B. The problem is, when you're doing the normal sampling process, you can't backpropagate through a stochastic node, right? The sampling node. And so what we can do is instead, we can take a random noise, mean 0, 1 noise, mean 0, 1, and we can scale it by something and add something to it and just basically take normal, take Gaussian, standard Gaussian distribution, and then shift it over by A and scale by square root of B, and that will give me exactly the same thing, right? Exactly. So I can get my mean of A, variance of B without directly sampling from it. I can just do it this way. So I can randomly sample some noise, I can add something to it, I can multiply something to it, and then I can backpropagate through all of this, no problem, because the stochastic node is no longer in the way. So if any of this seems new to you, just go ahead and take a look at that video, right? Because I do a huge deep dive into this stuff. So let's go ahead and write that sample z method. Def sample z, self mu log var. It's going to be sigma. So we have the variance, or the log variance. We want the standard deviate, right? So we want sigma. So we're going to do torch.exp 0.5 times log var. So this will give me sigma, right? We can you can just do the math. I do the derivation again there. We can sample some noise. Torch.rand and like sigma device is sigma.device. D type is equal to sigma.d type. Just make sure it's all the same. And then z is going to be mu plus, or mu, sigma times noise, return z. And that's it, right? So this is how I can sample data. Because again, remember, our mu and log var came from learnable parameters, right? These are learned projections of data. So I can backpropagate through this, no problem. There shouldn't be an issue there. But if I had actually sampled from a distribution with mean, mu, and log var, so if I'd done like torch dot normal and then passed in the mean, then we can't backpropagate through the sampling process, right? So this is the reparameterization trick. Good, so that gives me z. And now here's a key part. If scale factor is none, we can do a quick check. If self.config .vae scale factor is not none, scale factor is equal to self.config.vae scale factor. So we're going to have these things, these scale factors that we're going to multiply by. Right now, you can see that I have them right here. These are some pre-computed constants. Now, why we compute these and the purpose of them, I will not talk about just yet, right? We'll kind of get back to this later. In the original implementation of the, from Stable Diffusion, if you look at their AutoEncoder KL, they have their own constant here, right? They have their own constant that they've pre-computed for their specific model. Well, I've also computed them for our model, and we'll see how we compute these a little bit later. But it's to make sure that we have unit variance, right? So we'll talk about it later, right? We won't go into it right now. Otherwise, we're going to assume scale factor is just 1 by default. We're going to take z times scale factor. We won't have this, by the way, during training. This won't matter right now. This matters more for later when we train the diffusion model. So we'll see it then, right? Our output is going to be the posterior is z. And then if return stats, then we can do output mu is going to be the mean vector. Output log var will be the log var vector, or not vector, these are tensors, right? Return output There we go. That's our encoding. Nothing too crazy. Again, we'll dig into the details of this later when we actually see it. To decode, self z, again, scale factor is none. So there's two options, right? We can either pass this constant in the method, or we can define it, or we can set it in the config, and then it'll use it from there, right? So both are available to us, and again, we'll talk about it in a bit. But just the same way, if scale factor is none, and this is the same chunk of code from before, if we took z and scaled it by a factor here, we need to unscale it before we pass it through the decoder. This scale factor that we're doing here is done after training. So the model was never trained to, or basically the decoder was never trained to see this scaled version of z. It's been trained to see the original z. So if we scaled it for some reason after training, we need to make sure we unscale it here before we pass it to the decoder. And we'll kind of see all that later. Z is equal to z divided by scale factor. X is equal to self dot forward decoder z, should be x. Technically it's x tilde, right? It's our prediction. And we return x, just like that, right? So again, we'll dig into this later. And so our final forward method, def forward self x, we're going to do output is self dot encode x, return stats is true, right? We need that mu and variance, log variance. The reason we need mu and log variance is we need to compute the loss, right? So we'll do that in a second. Reconstruction is equal to self.forward decoder output, and we're going to pass in the posterior, right? Basically pass in z. And there we go. We're going to pass that in. And now we are going to just store. We're going to need all this later. So reconstruction, just store this as a, just store it in our dictionary. Remember, output here is a dictionary. We're just going to keep adding stuff to that dictionary so we can use them later. And we need our KL loss. So it's going to be self.KL loss, output mu, output log var. Right? That's what we need. And then we're going to store output KL loss is equal to KL loss return output. So let's go ahead and define this self.kl. We need to write the method, right, to compute KL loss. This is the standard KL loss function. So we already derived it. It is, if you follow this derivation, it's this right here, right? So it's basically this part right here. And then this is the reconstruction term, which we don't care about right now. So we just care about this, right? That's the main piece. So we're going to do def KL loss self mean log var. And the whole point of the KL loss is it's a regularization term. We want to incentivize the model to organize the latent space such that it's somewhat standard Gaussian, right? And that's basically what we have here. So our variance is going to be torch.exp log var, right? It's log, so if we exponentiate, it gives us our variance. And our KL loss is going to be negative 0.5 times torch.sum. Remember, our data here is in the shape of batch by channel by height by width, right? That's the latent space, right? So whatever the latent channels is by the latent height and width. And so we're going to add together 1 plus log var minus mean squared minus var, right? So minus variance minus mean squared plus 1, and then that log of the variance, right? So that's the formula. Yeah, that's the formula. And we're going to add it up over 1, 2, 3. So basically, we're going to take this this batch by channel by height by width, compute the pixel-wise in the latent dimension, the pixel-wise KL divergence, and then add it up over the height, width, and channel dimension, which means all I'm left with after we compute the loss is going to be a vector of length b, right? So basically, we'll get the per sample KL loss, and we'll see what we do with that later on. Return KL loss. And that's it. That is our entire variational autoencoder implementation, right? Nothing too crazy. So now that we have all this, and just to make it a little bit clear, this is the original source code that you can go ahead and take a look at. We also have the VQ VAE in here, which does a lot of the same things, but it's it's training a quantized version. This is pretty close to the VQVAE tutorial I have, so nothing too crazy, but I don't want to add additional complexity when this is complex enough, right? Good. So now that we have that, let's talk about the next piece. We have the VAE, we have our LPIPS, we have our discriminator, the PatchGAN. I did forget one thing. Our discriminator, the traditional initialization for GAN discriminators is our normal Gaussian. So let's just add that in here right here. Def init waits module if is instance module nn.conv2d, then nn.init.normal module.wait.data 0.0, 0.2. That's the standard mean standard deviation initialization. In the same way, we'll initialize our batch norms the same way as well, right? So this, again, standard initialization for our for GAN stuff. Okay, good. So now that we have all of that, we have our discriminator, we have LPIPS right here. We have LPIPS. We have our transformer. Specifically, we just have attention. We have our VAE. So I think we have everything we need for stage 1 of our training. Let me double check right here. Yeah, I believe so. Okay, perfect. So yeah, the first step is we need to train. Now we need to actually do the training. So stage 1, like I mentioned, the LDM, latent diffusion models, have two stages of training. The first stage is training of the variational AutoEncoder, right? This part right here. And then the second stage is training the diffusion model on the latent space of that variational AutoEncoder, right? These are the 2 stages of training. So we're going to do stage 1 today, and then next time we'll implement the UNET, and then we'll do stage 2, right? To do all this, let's make sure that this import works fine. So let's do new file. This is going to be called stage1 VAE trainer.py. Let's see. Utils. Okay, I need to work on that. We need to write some helper methods. And we also need this LDM config. So let's work on that real quick. So like I mentioned, we have that YAML config file, but it'll be a little bit easier if we just have like the way I typically like doing it with the data classes. So we're going to create another file in our modules right here called config.py, and I'm just going to paste this in, right? There's nothing interesting in here. This is just the LDM. So everything we need for the variational AutoEncoder, all of this information's here. It will also be loaded by that YAML file later on. And then we also have all this stuff for the UNET here, but we are not touching any of that right now, right? We'll get there later. And we also have extra stuff in here for quantization, which I'll leave in there just so it doesn't break any of the code, but we won't be using any of that stuff. And this is that VAE scale factor, which we haven't talked about yet, and we'll see that later when we actually go to compute it. So now that we have all of this ready to go, that's our config, we can go ahead and start. Oh, I need to add it to the init as well. So it'll be from config import LDM config, just so it's there. Just be .config. Good. And everything here should now import just fine. All right. All right, so let's go ahead and start the training loop. I actually made a little bit of this video already, but then the power went out, so I'm having to start over again. Just a couple of small things. So I had to make there's a few small bugs in the model. I think there was a spelling error somewhere. And the main bug was this one right here. Basically, in the encoder block, the number of input channels to the downsample block here is the output channels. I believe that's what I changed. So there was a couple of super tiny bugs here and there. I believe that was the main one that I caught. Other than that, we should have been good. There was a spelling error in one of these layers, but I can't exactly remember what it was anymore, but it's fine, right? So you should, when you're watching the video back, you'll probably catch it while watching it, and you can comment, and that's totally fine. And I'll make sure I mark it later. But yeah, for now, this should be fine, right? We have everything we need. So So let's go ahead and start writing our model stuff out, to the training loop out. And so let's, I'm just gonna go ahead and just paste in all of this extra stuff here. So these are just standard imports. We'll be using Accelerator for distributed training. We'll have our scheduler right here. And then we have our, essentially we have our, all the stuff that we built, the Variational AutoEncoder, we have the config file for LDM, PatchGAN, its initialization. We have our own LPIPS. We have the get dataset to actually load the dataset, the conceptual captions I'll be working on. And we have all of our, standard set of like experiment name, the weights and biases run, the working directory, all stuff, resuming, training config, model config. These are the two we really care about. We have our dataset, path to dataset, and path to savegens. So, and after that, we have our actually running things. We'll be using this file, which has everything, right? So experiment name, the working directory, where our configs are, the dataset. So that's basically, the actual calls for everything for this arc parse here. So to do this, this is going to be relatively straightforward. We're going to start with our just loading all the config files and preparing everything. So we're going to do with open args.training config r as f. We're going to do our training config is going to be YAML.safe load f, and it'll be the training config. And again, just to recap, that was this file right here, right? So basically all the stuff we need for this specific training config. So we'll be loading like our optimizer stuff, our learning rates, and the KL weight, and everything else from here, right? So we'll kind of reference this as we're going. Similarly, we'll have our with open args.model config r as f. We're going to then do VAE config is YAML.safe-load f, and we're going to grab specifically the VAE, because if you remember in our LDM config, we have both the definition or the structure for our variational encoder, and then we also have it for the UNET, right? So we have both of them. So there we go. And we can then go ahead and do our config. The actual config we care about will be the LDM config that we had defined in this file right here, right? And we have our definition for the VAE stuff right here. So that's what we're essentially going to load in. So we're going to do our LDM config, and we'll pass in our VAE config definition right there. And yeah, so after that, we just need to load a couple of things. So I'm going to just paste these things in. This is to load that path to experiment, right? So the working directory to the full experiment directory. We have our accelerator that we're initializing here with how many gradient accumulation steps we want, weights and biases if we want it, and then logging, that sort of stuff. So we're just going to keep all that right there. And then we're going to load our model. So that's the VAE. We're going to pass in that config file, and we're going to do .to accelerator.device. And just to test it, we're going to do ran.torch.randn 2 by 3 by 256 by 256. That's kind of the expected shape of our images that we'll be passing in. 3 channels, 256 by 256 each. And so we do our out is model ran. If we print out, and if we do reconstruction.shape, that will give us the shape of the output reconstruction. If we do print out and like the log variance dot shape, that will be the shape of the latent tensor, right? So we can just go ahead and print those out and just make sure they are what we expect them to be. So we have training config. Let's just double check right here. This should be, this should be training args, not config, my bad. Okay, let's see if that fixes it. Okay, and we need to make sure this is on .to accelerator.device, right? Has to be on the GPU, just like everything else. There we go. So our reconstruction is 2 by 3, 256, so same shape as the input, so that's good. And our latent space is 4 by 32 by 32. So it'll be 4 channels, 32 by 32. That will be the latent space shape, and that's why this is called 32 by 32 by 4. This, this run file that we have here. Good. So that's everything we need. And just to make this clear, we can do a quick. Our latent res is basically to compute it, right? Res is just going to be our config dot image size divided by 2 to the power len of the VAE config.vae channels per block minus 1, right? Because remember, the VAE channels per block, if we go right here, we have 1, 2, 3, 4. So we have 4 of them, and we downsample in all of them except for the last one, except for the last one. So that means it's going to be basically 3 downsamples. So we basically are doing a full downsample by a factor of 8. So we can, instead of printing out latent res, we can just put this nice little comment there just so it's clear, right? So that's basically what our final latent resolution would be, 4 by 32 by 32. Good. After that, we now need to set up the rest of the stuff. So first is our LPIPS. So we're going to use LPIPS. By default, it's going to be false. But of course, in our training arguments, right, in the training arguments right here, it's an option, right, whether or not we want to use it or not. And do we want to use the LPIPS package, or do we want to use our own LPIPS? If we want to use our own LPIPS, then we can pass in the weights of our own LPIPS, right? So it's completely up to us. So I'll just make it a toggle here, and you could either train your own LPIPS model and then use that model, or you can just use the LPIPS package, right? That from the patch similarity, like Git repo, right? So either one is optional, up to you. Training config, use LPIPS. So if training config use LPIPS, then we're going to use LPIPS will be then true, right? We'll set it to true. And we're going to do if training config use LPIPS package. So if we're using the package, then our LPIPS loss function is going to be equal to LPIPS.LPIPS. We'll use the VGG backbone.eval. Otherwise, we can use LPIPS loss function is equal to my LPIPS, and we're going to do LPIPS loss function dot load checkpoint. Right, load checkpoint, and we will load in the training config, and it will be the LPIPS checkpoint. So it's up to you. If you can just use the package. The performance of the two are identical to each other, right? So it doesn't matter which one you use. But if you want to do this, then you have to train your own, which we talked about in the first video. If you want to use the package, then just use the package. But either way, this is basically the model that we'll use to measure perceptual quality. Next, we have our discriminator. Use disk by default will be false, and we're going to do if, again, training config use PatchGAN. If we want to use PatchGAN, no problem. Then we're going to use disk is true. And we're going to do our discriminator. Nader is equal to, and I'll just copy this in so I don't have to type all of it out. It's just that PatchGAN model that we implemented in the first video, and we're initializing the weights like this and just putting it on the right device. Say the input channel start dimming, depth, kernel size, and the slope, right? So 0.2 for the slope of the leaky relus. One thing to keep in mind, and this is just a small detail, but if we look at our discriminator, PatchGAN has a bunch of batch normalizations in it, right? The problem with batch norm is it doesn't parallelize well, because if we're doing DDP like we're going to be doing here, that means we're processing batches but across multiple GPUs. So like if we have a batch that is 16, we'll have 16 on one GPU, but then 16 also on the second GPU. And when we do batch norm, it needs to be computed across all 32 samples, not just 16 of them. And so this batch norm needs to be converted to something called synchronized batch norm. This is why batch norm is not so popular for large-scale training, because batch norm just has this penalty that you always have to synchronize GPUs every step. But either way, we're going to throw that in there. So if accelerator.num processes is greater than 1, more than 1, then we're going to do our discriminator is equal to nn.sync batch norm.convert sync batch norm discriminator. Right, so this is going to basically loop through your model, find all the batch normalizations, and turn them into the sync batch normalizations, which synchronize across devices. So that's just one small step we have to do. Here's our first. So I mentioned we have some utils. I haven't written any of these yet, so let's just let's uncomment u, and then put u right here, and then comment u out, and then in our utils right here, I'll just kind of paste in the utilities as we're going. This one's easy. This one just counts the number of parameters and prints it out nicely. It's just nice printing of whatever, so that's fine. So this is going to go ahead and print out our number of parameters. Here we go, right here. And there you go. So let's just make sure all of this runs. If anything goes horribly wrong, looks like we're missing something. Cannot import generic image dataset. That makes sense. In the utils, we don't actually define in our dataset here. Like I mentioned, in my actual dataset, in my Git repo, you'll find more supported datasets. We just wrote the conceptual captions one, right? So I don't have any other ones here. So we can get rid of that. Let's see if that works. There we go. So it loaded everything. So that's good. That loaded our model. And then we are able to print out the number of parameters. Our VAE has about 83 million parameters. So not big, but not small either, right? Good size model. Now that we have all that, let's load our optimizer. So our optimizer will be, I'm just going to copy these as we go so we don't have to type everything. It's just our standard atom, all the learning rate, the beta 1, beta 2, all that stuff, weight decay, it's all defined inside this file, right? All of that stuff's right here. So we have everything defined for the optimizer, but of course, this is the optimizer for our model, the VAE. If we have a discriminator, right, the discriminator, the PatchGAN, will have its own optimizer, the disk optimizer. So we can define that here as well. And again, that will have its own set of learning rate and that sort of stuff, right? So we're just gonna stick it all right here. Good. After we have all that, we need our data loader. So this is it's gonna be easy. So it's our mini batch size. It's gonna be the training config per GPU batch size. So that's how I'm gonna do it. I'm gonna define the batch size per GPU. And then after we have it per GPU, then if you're training on 2 GPUs, then the effective batch size will be double. If you're training on 10 GPUs, then the effective batch size will be 10 times as much. Training config, gradient accumulation steps. So we're going to separate it up into that many gradient accumulation steps if that's set in the config. And then our data set and our collate function is going to be equal to, and I'll just actually copy this in so I don't have to do all this. So this is that get dataset method that we wrote in our dataset file, which was right over here, right? So that was the get dataset method, right? And we don't really have any of this stuff right now. Yeah, that's fine. Okay, yeah, we don't really care about any of those things right now, so we're good to go. So we're getting our dataset, and by default, we're going to return caption as false because we don't need the captions here. And we can go ahead and just print out the number of training samples. After that, we can load our data loader. So I'm going with pasting, pretty easy. Our data loader is just, a wrapper on the data set. And one thing we might be wondering is, well, how many epochs are we training for? So I don't like training by epochs. We'll be training by steps. So you can see that we'll be training for 500,000 training iterations. Just to compute the number of effective epochs, we can do that really easily like this, right? So it'll be how many samples per GPU times the number of GPUs is how many are we processing per step. How many steps are we processing for? That's how many samples are we processing in total over 500,000 iterations. And then divided by the length of the dataset gives me how many full passes to that dataset we'll have. And we can go ahead and print that out as well. After that, we have our scheduler, just like we did for the optimizer, right? We had we need the regular scheduler, which again, we're setting right here. We're just going to use constant with warmup, constant with warmup. So it'll just warm up to some given constant over some number of warm-up steps, which is also provided, how many learning rate warm-up steps we want. And then we just go ahead and load them. And again, for the discriminator, we'll need exactly the same thing. And so now that we have all of this, we can do our accelerator.prepare. So we have our model, optimizer, learning rate scheduler, and our data loader is going to be accelerator.prepare, model, optimizer, learning rate scheduler, and data loader, right? So that's it there. Now, if we're using the discriminator, that means we have extra things to prepare. We also have the discriminator, the disk optimizer, disk learning rate scheduler is going to be accelerator.prepare. Again, the discriminator, disk optimizer, and the disk learning rate scheduler. So model, optimizer, yep, that's everything. And then if we're using LPIPS, right, LPIPS is also just a model. So our LPIPS loss will again be accelerator.prepare prepare LPIPS loss function. Right, so there we go. If we're using LPIPS as well. Now that we have all that, we're going to load some validation images. I don't actually have any on me right now, but it doesn't really matter. So basically, this is just in case you want to inference some images as we're training, so you can keep track. So how this is going to work, even though I don't have it, is basically in this file, in our training file, we have this, where is it? Val image folder path. Basically, it's a folder full of images that we want to inference as we're going. If we don't provide this, then we'll just randomly sample some images from our data set and inference those as well and plot them, just so we can see how the model's doing as we're going. So this is optional if you want specific images or just, if you just want a random sample. This is just a very simple method in our utils. All we're going to do is give it the path, the image size, device, and dtype, grab all the images, grab all the image files. Here's those image transformations that we've implemented earlier in the dataset, right? In the dataset file, we implemented those image transformations. Go ahead, load them, convert them, transform them, stack it together, and it's basically just a batch of images that we will be inferencing in the future, right? So there's nothing too fancy about this code. But now that we have that here, we can go ahead and uncomment U. So we have this method as well. We just don't have the saving one yet. We'll get to that later. Again, there's nothing fancy about it. Okay, so now that we have that last part, we have some model logging. So this is going to be our model log and our discriminator log, and we'll see exactly what each of these things are as we're implementing them. But one thing we want to do is our reset log. This is just going to be a quick helper method. Will be return key 0 for key blank in range, or not in range, in log.items. And there we go. So that'll just go ahead, if we pass in a log, we can reset all the values to 0. This is where we're going to accumulate stuff, and you'll see all that happen. We also need to be able to resume from checkpoint. So if args.resume from checkpoint is not none. So if we pass in a checkpoint to resume from, the way I always do checkpoints is it's going to be essentially like the path to the checkpoint, and the checkpoint name will always be like checkpoint, and then like the iteration number here. So it'll be underscore iteration. So if like we're on the 10,000 step, then it'll be 10,000 and all that. So this is relatively straightforward. So we'll do accelerator print resuming, and here I'll just actually paste. I'll just keep pasting it. No one wants to see me type this stuff. So we can go ahead and resume from checkpoint. We have the path to the checkpoint, right? So it's path to experiment, inside which there'll be a bunch of checkpoint files. We'll do accelerator.load state. That will load everything in, all the checkpoint files, all of the optimizer states, everything we need will be loaded in. And we set the global step as if the name is, again, like checkpoint 10,000, that means we'll split on the underscore, and then the 10,000 is like the step that we're on, right? That's the step we're on. Otherwise, if we're not resuming, then the global step is 0, right? We haven't done anything yet. And finally, we have our progress bar. Just go ahead and initialize at the global step if we're starting halfway through training or something like that. And we just disable the progress bar for anything that isn't the main GPU. So we only need the progress bar once. So that was kind of boilerplate stuff, nothing interesting. Now for the actual interesting part, the training loop. So we're going to do while train model.train, start into training mode. And if we're using the discriminator, then we're also going to do our discriminator.train, throw that into training mode as well. And so for I, batch in enumerate Dataloader, pixel values is batch images .to accelerator .device, right? Those are the images that we're going to pass in. And here's where it starts to get a little bit complicated in the way that we're going to do it. There's essentially a couple of stages to training, or like within this first stage, there's a couple of things that's happening. So like I mentioned, in our discriminator, the way that it's set up for a lot of implementations is that we actually don't start training the discriminator until 50,000 steps have passed. So this means basically our model, if I pull back that figure again, give me 1 second. So that is right here. If I pull this figure back right here, in this entire VAE setup, right, we have our KL loss, reconstruction loss, that'll always be there. We have the LPIPS loss, but then we have this GAN loss. And for the GAN, we need to train this discriminator. But the way that it's typically trained is we really don't kick the discriminator in, like we don't actually use the discriminator until the VAE gets reasonably good at reconstruction. It might not be great, right? It won't be perfect. It might have like a lot of the problems that we've talked about for VAEs, but still reasonably good. And so what we're going to do is delay the training of the discriminator until we get to here. But when the discriminator does start training, then we're going to do the standard GAN setup. The first one step will be to train our VAE, and one step will be to train the GAN. So for the first 50,000 steps, we're just going to train the VAE. After 50,000 steps, we're going to toggle back and forth. One step here, one step here, one step here, one step here. So we'll just flip back and forth between the two until we're done, right? Until we've trained for all the steps that we want. This is, again, so we just have to add in a couple of little extra flags here. So first, we'll do the model toggle. This is going to be global step. If we want to flip every other, just check for even versus odd. Right, so the model toggle will just be that. Are we on an even step or odd step? And then our train discriminator will be whether or not the global step is greater than or equal to the training config. And this was the disk start, right? That's what we called it, disk start for 50,000 steps. And so that just tells me, right, which step, are we on an even step or odd step, and are we training the discriminator? And so we're going to do if not use disk. If we're not using the discriminator at all, then it'll be generator step is true, and train disk is false. Right? If we're not using the discriminator, then it's always going to be the generator step, like, and the generator being the VAE here, right? Otherwise, else, if use discriminator is true, then if model toggle is not, if model toggle or not train disk, train disk, then we'll do generator step is true. Else, generator step is false. And that's how we're going to switch between the two, right? So if we are on an even step, or we're not training the discriminator, because again, initially at the very beginning of training for 50,000 steps, we're not training the discriminator. So the generator step will be true for all 50,000 of those steps. Once training disk is true, then this has to basically, this is going to start flipping, right? Basically, this will decide whether or not we're doing a generator step or a discriminator step. And that's essentially it, right? Nothing, just a little bit of housekeeping essentially. And now we can do model outputs is going to be our model, pass in those pixel values, and our reconstructions is going to be equal to the model outputs, reconstruction. And that's it for the model. Now it's time to do all of the hard work of the actual, managing everything that we just talked about right here. So we're going to do if generator step. So if this is a step where we're training the generator, which it will be for, for the first 50,000 steps, we're going to go ahead and just zero out the gradients right now, because the optimizer refers to the generator, the disk optimizer refers to the discriminator generator, or the discriminator optimizer. With accelerator dot accumulate model, so this will handle the gradient accumulation flag for us, so that'll be convenient. We're going to do a couple things. If training config reconstruction loss is L1, then our reconstruct, here I'll just actually paste this so I don't have to type this 3 times. Basically, if in our training config I have it set where the reconstruction loss can be L1 or L2, so basically L1 or mean squared error. So there we go, that's our catch there. If we're doing L1, then use L1 loss. If we're doing L2, use L2 loss. And it'll be between the reconstructions, right, the thing that came out of the model, and the input to the model, the original pixel values. And that's it. After that, we have our LPIPS loss. So L is going to be, and this is going to be a, this is something we typically have to do for DDP, but if you don't do this small step, then it throws like an error about gradients not existing on specific GPUs. We're just going to set this to 0. Torch.zeros size, and then device is equal to pixel values.device. I'm just going to put that in there just in case, because if use LPIPS is false, or if we're not using LPIPS, then LPIPS loss is just 0 and it doesn't matter. If we don't have this, it just throws a warning every time that something doesn't exist. I can't remember the exact warning, but that's fine. We'll have our LPIPS loss function, reconstruction, and actually let me just double check right here. It should be LPIPS loss function right here. LPIPS loss function, and we're going to pass in the, not the reconstruction loss, but the reconstructions, right? The reconstructions. And that's it. And we're also going to pass in the original images, pixel values, and we'll just average those together. Because again, this is a measure of perceptual quality, right? It's the perceptual quality, and we want to make sure that we're maximizing, or basically making the difference between these two as perceptually similar as possible. So there we go. So that's our LPIPS loss. And now we're going to do our perceptual loss is going to be the reconstruction loss plus training config, LPIPS weight times our LPIPS loss. So in our file here, we specify for LPIPS, for example, right here, the weight. We're going to use a weight of 0.5. I got these weights off of the CompViz, like the official Stable Diffusion repo, right? They use 0.5, I believe. So that's what we're doing here, perceptual loss. And then our loss is going to be the perceptual loss. So I'll just keep a copy there. Now we're going to compute our discriminator loss in case we are training the discriminator. So we're going to do our gen loss is going to be torch.zeros, just like we had. Size is just an empty tensor, it doesn't matter, there is no size. And then device is going to be our pixel values dot device. And we also have something called the let me make it be better. Adaptive weight. Again, this is going to be the same thing. Now let's talk about the adaptive weight a little bit. And I actually would recommend you trying it with and without, because you'll see immediately the difference. As our model's training, right? Remember at the very beginning of training, at least for the first 50,000 steps, all of this stuff here doesn't exist, right? None of, let me delete all of it. All of this doesn't exist. All we're doing is training based on this loss. We want to minimize the reconstruction loss and minimize this LPIPS loss. And we have the KL divergence loss, which we haven't included yet, but we will in a bit. Now, as this model gets better and better, right, these loss values should get smaller and smaller and that sort of stuff. And this model will get pretty good at reconstructing. After 50,000 steps, we've suddenly introduced this new thing, this new source of gradients. And you can imagine that initially this discriminator doesn't know anything. So it's going to be getting large loss values and it's going to propagate those gradients into our model. But if this discriminator is propagating large gradients to the model, it will basically push the weights here completely off, right? Basically, it'll take the weights of this model and just completely throw them off. It'll shift them because we're passing in large gradients that have showed up out of nowhere because this model doesn't know anything yet. And so this is a little bit of a problem. If you train a model like this, what you'll see without this adaptive weight scheme, which we'll talk about in just a second, what you'll see is that your model's going to get pretty good at reconstruction. And you'll see, like, you know, every 10,000 steps or whatever, you'll make a plot and, okay, the reconstructions are getting better and better. But once that discriminator kicks in, your reconstruction will become immediately garbage. Like, basically, it just won't look good anymore. And the model will have to, again, basically update until it gets good at it again. That's basically the problem. And that's happening because you've kicked in this new gradient. You have new gradient information coming in. And these gradients should be relatively large at the beginning because they don't know anything. So they haven't converged or anything like that. And because of that, it's going to take all the weights of the VAE and just completely throw them off from where they were. And that's a problem, and we want to avoid that. The adaptive weighting scheme is basically this. When we backpropagate, we're going to do something, we're going to do a quick calculation. We're going to check the derivative of the loss, which is basically these three things, right? KL, or basically our perceptual losses for now, the reconstruction and LPIPS loss. We're going to do the derivative of these losses added together with respect to this last layer, right? With respect to this last layer right here. That's going to have some, gradient value. What's the derivative of this perceptual loss with respect to this? Then we're going to check what's the derivative of our PatchGAN loss, right? This loss right here, also with respect to this, with respect to the last layer of our model. You would assume, right, and we would assume that initially at the beginning of after 50,000 steps, at the beginning of training of the discriminator, the PatchGAN loss, the gradient that it produces, will be much, much, much larger than the loss created from the reconstruction plus LPIPS, right? We'd expect that because the PatchGAN doesn't know anything, so it's just feeding in, large gradients initially as it's optimizing towards the right answer. And so what we can do is essentially weight them, right? We can weight down the gradients coming from here just so they match, right? So we're not like completely destroying the parameters here by introducing kind of these new gradients that don't know any better. And so let's kind of just look at it in practice, and it'll make a lot more sense then. And so initially we're just going to initialize these things as zeros, just so in case we don't use it, then it doesn't throw any kind of any warnings. If train disk, we're going to do our generator loss is going to be -1 times the discriminator reconstruction dot mean. So we'll see exactly what that is in just a second, but basically the goal of our reconstruction, right? We're basically passing it in, and we want our generator to fool the discriminator, and so we're just basically flipping him around, right? -1, it means we want to essentially go in the opposite direction. That's why we're multiplying by -1. We'll see exactly how this plays in just a second. The reason we're doing this is so we can compute our adaptive weighting scheme. So how this is going to work is we're going to do our last layer is going to be, because we're doing it in DDP, we need to quickly unwrap the model. We're going to unwrap the model. And then the very last layer would be in the decoder .convout.weight, right? That's the last weight layer we have. If we look at our VAE, right, the very last VAE, it will be in right here inside the self.decoder, and then inside this decoder we have VAE decoder. Let's go up to the VAE decoder. Inside the VAE decoder we have our conv out. So that's the final layer that outputs the final output to our model. So that's the last layer of the model. And what we're going to do is compute the gradients with respect to our losses. So the first will be norm grad with respect to perceptual loss is going to be torch.autograd.grad. So this is how we can manually compute gradients between things. The outputs is going to be the loss. The inputs is going to be equal to the last layer. Last layer, right? So basically the weights of the last layer. So I want the derivative of the loss with respect to this, essentially. And then we're going to do retain graph is true, right? So we don't lose that information. We're going to index it because it returns a list. Detach because we just need it as a constant. And then we're going to normalize it, right? L2 norm. In the same way, we're going to do norm grad with respect to our, norm grad with respect to the generator loss. This is going to be, again, torch.autograd.grad outputs equals, again, in this case, it will be the gen loss that we just computed right here, right? Just pass data into the discriminator to the generator loss. We have our inputs, same is equal to the last layer. Again, retain, and everything else is the same, right? So I can just paste this in, right? Again, retain graph is true. Index it returns a list of things. So we describe the first thing, and then we detach, and then normalize. And what we're going to do is our adaptive weight is equal to norm grad with respect to perceptual loss divided by norm grad with respect to gen loss, and we'll just clamp it. Min equals 1e minus 8, just so we're not dividing by like 0 or something like that. Now that we have that, this basically tells us what we have, right? This is essentially the ratio of the gradients, so coming over here, it's the ratio of the gradients from our discriminator versus the gradients from our perceptual losses. As we see here, from the basically our discriminator loss from the discriminator here is in the denominator. So when we have a large gradient coming from this PatchGAN loss, when it's a large gradient, then the ratio becomes small, right? It becomes small. And when this is kind of smaller, then it gets bigger. So this means the adaptive weight at the beginning, we would expect it would be a very small number because we'd be dividing by a very large gradient here. But this allows us to dynamically adjust our weights. Another quick trick, adaptive weight, we also will just go ahead and do a quick weight.clamp max is equal to 1e4. So we're going to make sure it's no bigger than 1 to the power, right? 1e4. And so then our loss is going to be equal to finally the loss plus the adaptive weight times the gen loss times the training config disk weight. And that's basically it, right? Nothing too crazy. All we're doing here is we're dynamically managing the magnitude of these weights coming in from the discriminator, so we don't just like ruin all the weights that my model's already learned for the last 50,000 steps. And that's it. And basically this is a very simple generator loss. All we want to do is maximize, the generator wants to move in the direction of fooling the discriminator, and this will make more sense when we actually write the discriminator loss in just a second, which will just be the hinge loss. So we'll see that now. So let's go ahead and just keep going. We're going to do our KL loss, of course. KL loss is going to be the model outputs. This will be KL loss, and we had it per sample. We can go ahead and just average them up right here, just so we have that. And our loss is then going to be loss plus KL loss times the training config, KL weight, right? And by default, this is set to that, right? So that's the KL weight that we'll be using for this training. And it's pretty small, but it basically incentivizes some regularization of that latent space. We can finally do accelerator.backward loss. That will compute gradients. We're going to do a quick if accelerator.sync gradient. So every time we're done with gradient accumulation, so that's what this accumulate is doing. Every time we are done, so we're syncing the gradients, then we can do a quick accelerator.clip grad norm model.parameters 1.0, right? Just standard, making sure there's no exploding gradients. Optimizer.step, learning rate, scheduler.step. And then we have our log, and we can accumulate it in. So I'm going to do that right here. So our log, store everything in, and then for every single one of these things, we're just going to add it to our model logs up here, and then divide by the number of gradient accumulation steps, just so it's clear. We just average up over all the steps that we took, and that's it. Okay, else. So if we are if we're doing the generator step, this is training the generator to do our perceptual loss, fooling the discriminator, and that sort of stuff. Otherwise, we are doing it the other way. Disk optimizer dot zero grab. We're gonna go ahead and zero out our discriminator, and then just like before, accelerator dot accumulate discriminator. So we will be using the hinge loss here because that's what they use, but you could really use any GAN loss. You could use the Worcesterstein loss, standard GAN loss, whatever you want. But I'm just following the implementation as close as possible, just so it's relevant. So like always, discriminator, pixel values, and then we're going to do our fake is the discriminator reconstructions. Reconstructions. And our loss is going to be f.relu 1 plus fake plus f.relu 1 minus real dot mean. So what this loss is doing is basically incentivizing the separation of real and fake. So the way you can think about this is essentially, we know that we want to minimize this, right? We always want to minimize the loss. And so for ReLU to be min is basically 0, right? The smallest value ReLU can be is 0. That means we basically want 1 plus whatever the values are for fake to be less than 0, which means we want fake to be less than or equal to -1. In the same way, we know that in this one, in this ReLU, again, this has to be less than 0. Well, we want real to be greater than or equal to 1, because if real is greater than or equal to 1, then this whole thing will be 0 and we're good to go. So the minimum this can be is 0, this whole loss value, right? So as long as fake is less than or equal to -1 and real is greater than 1, then we're good to go, right? That basically will go ahead and cover that's basically how we can minimize this loss. That's what this is incentivizing. And that's basically it, right? That's all we want, and that's why we're using the hinge loss here. And hopefully that makes this a little bit more clear, right? Because what we want is essentially when we pass in the reconstructions into our discriminator, it's going to output some values, right? And with these values, we essentially want to make sure that our generator is making our model think, right? Making the discriminator think that the thing from the generator is real. We want it to think it's real. So we just want to move it in the opposite direction, right? We're going to basically flip it around, and that's exactly what we're doing, right? Nothing too crazy. We're just flipping it around, just so we're following this. But this is essentially the loss function, right? Our loss function for the discriminator. So now that we have that, we have our loss. We're going to do accelerator.backward loss. And we're going to do, again, just like before, I can copy the rest of this in. Right, just update, log it, store it, and that sort of stuff. Now that that's all done, we can do a couple more things. Now we basically have to log because we're essentially doing an accumulation here. We're doing with if generator step with accelerate, and here we go with just making sure I'm getting the tabbing correct. All right. So now we can do if accelerator dot sync gradients. So if we're, again, at the end, once we're done synchronizing, we've done all our gradient accumulation steps, then we're going to do, if we updated the VAE, we're just going to do a bunch of logging stuff here. So we're going to do if model toggle or not train this. So if we're training the discriminator, or if we're not training the discriminator, or if we're training the generator, right, based on the model toggle, then we'll do I'm just going to paste this stuff because it's all printing, so there's nothing interesting. It's going to be, we're going to first do accelerator.gather for metrics. Remember, this is these values exist on all GPUs, so we need to gather them across the GPUs and then average them together. That's what you see me doing here. We have our log, model log. We're going to go ahead and just add learning rate to it. Based on whatever our learning rate is right now, this is just going to go ahead and print everything out really nicely. We're going to print it. We're going to push it to weights and biases if we want to save it there. And then we're going to do a reset. We're going to reset it and get rid of that learning rate thing. And we're good to go, right? That's all. And we're going to do exactly the same thing for the discriminator, right? So again, we're going to do else. If we updated the discriminator, that's also fine. Go ahead and grab everything, print it, log it, and then reset it. And then after we're done, we've completed one full step of training, and we can update our progress bar. And that's essentially the end of the main training loop. Now everything else is just a little bit of logging, visualization, that sort of stuff. So what we're going to do is if global step percent training config, and we have our val generation frequency. So that'll be like this. Here, I will do that right here, right? So val generation for how often. So in here, I think I have it set to every 250 steps. We want to test a generation. So on the main GPU, we can do if val images is none, which is fine, right? At the top, like I mentioned up here, we can pass in some optional folder full of validation images, wherever that was. This was our, where did it go? Did I lose it? It was right, there you go, it's this right here, just missed over it. So yeah, we can optionally load some validation images if we want to. So we just have to create a folder ahead of time and store them in there. If it's none though, then we don't really have any. So we're going to do batch size is going to be len pixel values. We'll see how many we have. Why is this? Oh, there we go. So yeah, if every validation frequency on the main GPU, if we don't have any pre-created validation images, that's totally fine. We're going to do num random gens is going to be training config. And then we're going to do num val random sample. So that was my right here. So how many random samples do we want to plot per reconstruction? So I have 8. I want 8. And we're going to do if batch size less than num random gens, then we're going to do num random gens is batch size. So if we want 8, for example, and our batch size is just 2, then I can only do 2. So we'll just set that right here. No problem. And so then our images, images to plot is going to be pixel values, and we'll just index out the first num random gens. So however many we want. If it's all of them, it's all of them. If it's less, then we just grab as many as we need. Else, images to plot will be the val images, right? The ones that we already pre-computed and stored and prepped and everything. After that, pretty straightforward. We can just go ahead and throw the model into evaluation mode right here. And we can do with torch.noGrad. We can do reconstruction is model images to plot reconstruction, grab these reconstructions. And we're going to write our last, no, I'm not going to write it, but I'll just paste it in. This is just another helper method to create and save some images, right? So this is not helpful, or it's not even nice code, it's just whatever. So we can go ahead and pass in the original images, the generated images, and then the path to the saving, what step of training we're on, and then the accelerator. We can go ahead and create the folder if it doesn't exist for some reason. The first time maybe it'll run it. And then we can go ahead, grab our generated images. And the way we typically process it is pretty easy. Remember, our images are between -1 and 1. And so we need to make sure we scale it back to 0 to 255. No problem. We first clamp between -1 and 1, just in case, we have something smaller than -1 or greater than 1, but there shouldn't be after training for a while. After clamping is done, we go ahead and rescale it. So if our data is from -1 to 1, if we add 1, it'll go from 0 to 2. And then if we divide by 2, we're now at 0 to 1. Put it on the CPU. We permute it because we need batch size by height by width by channels, because that's how our plotting function expects it. And then we just go ahead, multiply by 255. That goes from, so my 0 to 1 is now 0 to 255. We bin it by converting to uint8, right? So standard 0 to 255 integer values for our images. And then our generated images are just going to be, we're just going to load them as images from array, convert them to RGBs, and store them. We'll do this also for the original images because we have to scale them from -1 to 1 to pass them into the model. We just need to unscale them right here. And then we're going to go ahead and just concatenate the images together and just make it look nice and plot them, right? So this is just boring plotting functions, nothing of interest. And so now that we have all of that, we can essentially just run that line right here. So just save them. And we need to go to the top and make sure this is an available method now. Should be. And now we have all of that, and we can throw the model back into training mode. And we want to make sure that, remember, this is happening on only the main GPU. We only need to do it once. So we're going to do accelerator dot wait for everyone. We're going to make sure that the other GPUs aren't doing anything. They're just waiting around for the main GPU to just go ahead and do this step right here. And now that that's done, we just have a couple of sanity checks, which I'll just paste in right here, basically just for logging and stuff like that. If our checkpoint iteration is either, if right here, we say that we want to save every checkpoint iterations every 5,000 steps. So if it's every 5,000 steps or the very last checkpoint, then go ahead and save the checkpoint. Otherwise, if we're greater, then say we're done. Train is false, break it. And if train is false, then this while train will exit, right? That's the end of the loop essentially. And that's basically it, right? So nothing too crazy. Let's go ahead and now fix this. So if there's any bugs, trailing comma not allowed. I didn't know that. Okay, not pre-GPU. Pre-GPU should be per. Per GPU batch size. Okay, I spelled something else wrong. Let's see. Let me just go here. Oh, it should be gradient accumulations step. That's my bad. Let's gradient accumulations step. Okay, I think I got that everywhere. All right, let's see if that fixes it. Might have still missed one. Okay, loaded the data set, and it should start training. Yeah, so you can see it's training now. This takes a reasonable amount of time, but you can see it's starting to train. Notice that all of our adaptive weights and stuff, like all of that stuff is not going to print right now, because this has to first train for 50,000 steps, and then after 50,000 steps, then the discriminator kicks in. Again, this helps quite a bit with stability, right? You want the VAE to be pretty good at generating images. And once it's pretty good, then the GAN kicks in and helps with everything else. So let's go ahead and just change this to, instead of disk start, let's make disk start 5. So after 5 steps, we're going to kick in the discriminator just to make sure that code is functional. So let's see here. Three, 4, 5. Oh, why did it not kick in? Did I do something wrong? Disk start. Let me check here. Maybe I didn't save. Disk start. Print accelerator.print this. And model toggle. All right, let's check now. False, true. Yeah. So disk start is still set to false. Global step greater than or equal to training config disk start. What is this? Am I not setting it in the right place? Sorry, I might have just missed a small thing somewhere. Oh no, it's still 50,000. What's going on here? Let me check. This is, okay, set it to 5 right here. What am I running? Stage 1 VAE, oh, this should be VAE train conceptual captions. There we go. We're loading the wrong config file. So now it should work fine. Two, 3, 4. There you go. So yeah, now we can start to see that basically we're training a discriminator step, a generator step, a discriminator step, generator step, discriminator step, generator step, so on and so forth. Right? That's the entire point of it. And this iterative method is all we essentially use for our and we really don't want to do this until after like 50,000 steps are trained, but this just gives you an idea. an idea of what we're trying to do here. So that's basically it. Again, to recap, the entire training loop is not all that complicated. It's the same KL and reconstruction from before, but we add on this additional LPIPS loss, which you can also see is being printed. Oh, maybe I don't print it separately. It's inside the perceptual loss. So yeah, we have this additional LPIPS loss, and then after 50,000 steps, the PatchGAN loss will kick in. When the PatchGAN loss kicks in, you'll start to see that we'll have, these are rounded down because it'll be pretty small, but we're going to essentially compute the adaptive weight. We want to make sure that the PatchGAN doesn't completely mess up all the work that we've done up till now by just throwing a huge gradient right at the beginning and shifting all these weights away from where they need it to be. And we kind of gently introduce them as the discriminator gets better and better by basically down weighting the PatchGAN loss adaptively. And this is actually a pretty common trick used when you have so many different loss functions that you need to manage, and you just need to somehow make sure that they all have equal amounts of effect. So now that we have all of that, we can do one more quick thing. It'll probably be a good idea just to write a inference script, right? An inference script. So let's write that. Inference VAE.py. And this is pretty straightforward. We're just going to do, I'm going to paste in this stuff. Model config, the path for the VAE backbone, and a path to an image, just so you can see what it looks like. And I can just start pasting. All this stuff is stuff we've already written, right? So we're going to load that model config, check the device, load that model. Now that we have the model, we can also load the state dictionary, right? Just so we can see the state dictionary, so we can actually load the weights, right? And I already have the weights saved in my working directory. I have a bunch of different weights, and we'll be looking at the VAE CC, and we have this model.safetensors, right? So that's what we'll be loading from. That's this. This load file comes from safetensors.torch, right? So we have everything we need there. And our setup will be pretty easy. Image will be image.open. And actually, we've written all this code, so I don't even need to type any of it. I'll just explain as we go. Load our image, convert it to a tensor, scale between -1 and 1, add the batch dimension, pass through the model, get the reconstruction. And after that, it's just plotting, right? So we're going to take our image, rescale both our image and reconstruction back to 0 to 1, clip them, and then plot them, and we'll be good to go. So let's go ahead and grab a image file. So I'm going to pass you right into here. So this is a picture of my cat. We're going to pass a picture of my cat into this thing. So we're going to do Python inference VAE, and our model config is going to be in configs, and it's the stage, or actually it will just be LDM, right? The LDM.yaml. We have our path to VAE backbone. This is going to be our, oh, that didn't work. Sorry, I must just press something back, so just paste you back. Path to VAE backbone will be in our, let's see, worker. It'll be VAE conceptual captions. Is, huge data set of a large diverse amount of images, so it seems helpful. And model.safetensors. And then the path to image will be the sample image.png. So let's see if this just works. There we go. So we can see we have an input image. Here's our output. So we get a pretty good reconstruction here. Right? Obviously a little bit different, but not bad. So yeah, that's basically it, right? You train the VAE long enough, it takes I think it said 100 hours here. It took about 30 hours on our cluster. So not the worst. The actual models are much bigger. There's one other thing we can actually try. How much does the domain matter? So for example, conceptual captions is a massive data set full of a large variety of image types. On the other hand, celeb A is just a data set of faces. What happens if we try to reconstruct my cat using the celeb A? It's actually something I haven't tried. Let's give that a try now. I called it VAE celeb A. How much does domain of the image matter? if we try to do a reconstruction on something that is never seen, and you actually see, turns out it works out reasonably well. You can see that the eyeballs here look more human, which is really weird actually to see. So it's doing something to the eyes and you get all this texturing, but the model seems to cross domains reasonably well. Like the fact that the Celebe dataset has never seen this type of image, but the fact that it still can do any kind of meaningful reconstruction is cool. Just the eyeballs are kind of weird. So okay, good. So that covers everything. That is our variational autoencoder. Now from the VAE, we need to essentially train the diffusion model. So going back into our image, right? This is the thing we're implementing or working towards implementing. We've essentially completed this red box here, right? This red box here. Now what we're going to do is train a diffusion model on the latent space of this VAE here. And there's going to be one thing we have to do ahead of time. We have to compute a constant to scale the latent space. We'll see why we do that next time. And then we, of course, have to train the diffusion model. But luckily, the training of this diffusion model is not any different than how we trained our diffusion models earlier, right? So we're going to be working on all of this next time. So I will see y'all then.